Good morning, afternoon, evening, everyone. Thanks so much for joining us today. My name is Alexis May. I'm Director of Content for AI Med. Before we get going with the good stuff this morning, I've just got a couple of housekeeping points to cover off. Just to confirm that all speaking sessions will be taking place here on the main stage. To the right of that, you will see our chat function. We encourage everybody to engage, send out your thoughts, comments, questions through on there, and we will endeavour to answer as many as we can during our sessions. Please do also check out the essential download section for additional content, including the 3 articles we'll be discussing during the Journal Club today at 1:05. At 1:25, we will be offering some gently moderated networking roundtable sessions. So there are 2 to select from, and again, you can see more information about those in the social section of the site. If you do have any issues with the platform, please contact my excellent colleague AJ at ai-med.io. As you hopefully know, AI Med is the only clinician-led movement dedicated to AI in health and care, and we seek to connect and educate clinicians, healthcare executives, and industry to inspire action and drive forward the deployment of artificial intelligence. To this end, and to complement meetings like today, we've developed the AI Med Connect platform to facilitate communication and collaboration between key stakeholders. The simplest way to access this is to search for AI Med on your app store and download the app, and indeed you will find that there is already a group and an ecosystem set up around cardiology, so that's all good to go there. That is absolutely enough from me. I'm going to hand over to Drs. Chang and Rumsfeld now to get things started properly. Thank you very much.
Well, welcome everybody, and thanks for joining us today. And I'd like to first of all thank the American College of Cardiology and Dr. John Rumsfeld for an amazing collaboration and for this effort, and also for GE for their generous sponsorship. So I am getting a pause button on my share here. Can you guys see my slides? Yes, good. Thanks, John. So I'm just going to give you a rapid whirlwind tour of artificial intelligence in the context of cardiology. And first, I want to give a special tribute to all of us, especially those on the front lines taking care of patients with cardiovascular disease. It's always good to reflect that we're in the middle of a historic moment and think about our colleagues. So I'm not used to having a meeting in this kind of situation from my room in my house. But I think looking at the moon set just a couple of nights ago, it does mean that we're in a brand new world, and we should really, really pay attention to how to benefit from the rapid change around us. So one of the things that we've been struggling with is the information overload, nothing more obvious during the pandemic. And as of 9 o'clock last night, according to PubMed, we've had 70,000 articles on COVID-19 and quite a few on cardiovascular disease. I think one of the reasons why AI has struggled is because we're dealing with a complex, not just a complicated situation. And anytime we have complex situations, particularly with healthcare, AI does seem to have some limitations unless humans are very, very much in the loop. And just a quick note that our formidable viral overlords are actually a good example of a complex adaptive system, which I think we need to be if we were to fight this virus. Another big problem is the data conundrum. And I think AI and COVID has demonstrated that we really need to work around the data and IT infrastructure issues that we continue to struggle with. I think on a positive note, I think AI is going to play a very important role as we find therapies for the virus. And this is a Google DeepMind involved with predicting the viral protein structure, just looking at the genomic sequence, and you can see very close to the real deal when they use artificial intelligence. And I think, as Antoine de Saint-Exupéry said, if you want to build a ship, don't drum up the men to gather wood, divide to work, and give orders. Instead, teach them how to yearn for the vast and endless sea. And I think that's how we could look at artificial intelligence. And we need a convolutional education. By that, I mean the clinicians that are here with us today and cardiologists really, I think, need to try to adopt artificial intelligence and data science as part of what we do to have essentially a new brand of cardiology, both adult and pediatric. And with that, we've, on the educational front, we've launched the American Board of Artificial Intelligence in Medicine, or ABIM, to help contribute the educational aspects. And I'll tell you that, that's the address. And we give 2-day comprehensive review courses. Yes. Okay. Let's see. I'm locked in here. Let me try that again. How about now? How about now? Okay, since we have a little glitch here, let's just, John, are you ready to go with your talk?
I'm ready.
You're not sure about the second in line.
I think you'll need to stop sharing yours. Yeah.
Yeah, let me try that. Okay. I can catch up after the break with some of the slides, but.
And are you able to see my slides?
Yes, we can see.
Yes, I can.
Okay, well, thank you, Anthony.
Go ahead, John. So I wanted to introduce John Rumsfeld, colleague and friend from the ACC, that we're also proud of as cardiologists, and really taking this on the artificial intelligence domain on as an important aspect of our future as cardiologists. So John?
Thanks so much, Anthony. It's a pleasure to join all of you. What a great setup today by AI Med to really talk about how we move from hype to reality in artificial intelligence and cardiovascular care. And I'm going to jump right in, cover a lot of ground. Anthony, I can talk a bit, and then we'll get right into the main program. I want to thank Alexis and colleagues, and Anthony and colleagues at AI Med for the collaboration with the American College of Cardiology. So I think we have to start by embracing that there has been hype. In fact, it's been about a decade of hype of AI in healthcare. AI predicts heart attack better than doctors. Your future doctor may not be human. This is the rise of AI in medicine. The problem is that it's been relentlessly predicted that this is going to fundamentally change healthcare for a decade. It has fundamentally changed one thing for sure, and that is the sector of startup companies in healthcare. There's been a unbelievable investment and proliferation of companies. It's a dizzying kaleidoscope of technology, of claims of what AI can do in healthcare, and the hype itself is almost overwhelming, especially when you move to the front lines of care, which still, despite billions and billions of dollars being invested, the front lines of care still look like this. Largely unchanged for decades. This is where care is delivered. There is no AI. And I like to say even the clock in the exam room isn't digital. So how can there be this divide between so much money and so much investment, so much AI hype and excitement, and the front lines of care? Well, Anthony alluded to it. Healthcare is complex, and it's fundamentally different than other sectors of the economy, both in its complexity, but also in the implications, meaning that if AI is not developed, deployed, and monitored correctly, it could cause harm to patients. And so we have to be more careful. And I think we need to embrace the challenges in healthcare. It's the old saying about innovation: fall in love with the problem, don't fall in love with the solution. And I think we have to fall in love with these challenges to overcome them to effectively and safely deploy AI in healthcare. And they all are real challenges, but they are navigable. And two, I want to particularly highlight that, again, Anthony alluded to briefly there, is that, first of all, we do require evidence. It can be preliminary evidence, initial clinical validation, then deployment and care, but we do need to build an evidence base for AI solutions in healthcare. And we really should be designing from together with the clinicians, with patients, with the idea of how it's going to be integrated into clinical care. Even as we evolve the way we deliver care, we should be designing it from inception, not just saying, here's an AI solution, you should use it. And I think we can dig a little deeper here to show what some of the challenges are. We see a lot of headlines. I already showed this headline: AI predicts heart attack better than doctors. Well, don't read the blogs or the hypes or the thought pieces about it. We need to start to look more seriously at the data behind it. And I want to give the investigators credit for publishing this is the article that led to that headline. But I think we have to be pretty circumspect about a lot of the results we're seeing. In this particular case, the use of machine learning added very little to the AUC, area under the curve, or C-index, in a predictive model, despite pouring in hundreds more variables. And what I think the conclusion is a bit overstated, because machine learning says significantly improves accuracy, but the problem is that it was no better than plain old logistic regression. This isn't the case in all studies, and the literature is growing, and I'm going to show a different one in a little bit. But I just think we have to be our own shepherds of how good is the evidence before we say that it's going to make a difference in health and health care. There are fundamental methodologic issues we need to at least understand here too. Leading thinkers like Frank Harrell asking if medicine is mesmerized by machine learning. He is mostly talking about the use of electronic health record or claims data going into all these AI predictive models, and pointing out that no matter how big the data is, that the underlying data quality is essential. And that the fundamental fact that AI does cluster analysis or classification or iterative pattern matching, while that may be very good for some parts of healthcare, we're going to get back to that, for risk prediction, that's not really necessarily the way we think in terms of clinical risk prediction. And on this issue of data quality, I don't think we can overstate it. Abraham Verghese, one of the great thinkers in modern medicine at Stanford University, has focused on this by saying good data is critical in medical applications of AI and machine learning. The messy nature of medical data, of the EHR in particular, makes the task difficult. Garbage in begets garbage out, sanitized, pretty, color-coded garbage, but garbage nonetheless. So what do we do? Let's pivot away from the hype and the challenges in front of us and think about the way forward. And I know the people involved in this conference today are at the least enthusiasts, and at most maybe actually directly involved in this. But I think we can think more about effective collaboration to move AI forward in a thoughtful way. And I admit, as Anthony alluded to, my day job these days is to try to move AI forward in cardiovascular care. So the data will continue to grow exponentially, healthcare data, digital data, and it's going to be higher and higher quality data. It isn't just EHR claims data. If you think about all the data in imaging and biosensors, biomarkers, a lot of this is high quality data, which then, if you think about AI as the umbrella term of the analytics we can use to deal with massive diverse data sets, to call out specific information, then I think we're thinking about it in the right way. Again, iterative pattern matching with this kind of data. Where is AI going to thrive going forward? And I would argue there's a spectrum, and it's a spectrum of application, and it's also a spectrum where I think it's going to happen faster, come to our frontline clinicians faster, and or is way off, may never happen, and needs the highest amount of evidence. So for sure, already there is AI actually already happening. It's in the software packages in our imaging software packages, for example. It's already in there to do things like edge detection, optimize image, estimate volumes and stuff like that. Imaging, I mean, it's coming fast and furious. The AI will help us at least pre-read or interpret at least parts of, if not whole studies. This area of risk prediction that gets so much attention, yeah, I think a lot of the prediction may come from imaging, where you'll see risk prediction based in the images, ECG, CTMR, CMR, CTA, echo, of course. And there will be progress made in risk prediction on things like EHR data as EHR data becomes more standardized and is improved. Dr. John Windle will comment on that in the next session. And I would just say that this far out idea of AI just replacing humans and making its own, I think AI can support in diagnostic and treatment decisions to augment us. But this idea it's not magic, it's math, and it's not going to replace it. This idea that it's just going to magically do it is wrong. It's a tool. And if we do get too far out to the right here of AI making independent recommendations, like to put in a defibrillator or something like that, it would have to have the absolute highest level of evidence. Now, I've shown some limited studies earlier. Let me show a couple more recent studies that show sort of the light at the end of the tunnel, not in any detail, but just to say that imaging is coming fast and furious, and we're seeing more and more are really well done published articles in cardiovascular imaging, moving towards automated interpretation of studies and risk prediction. And there are good risk prediction models. It takes a specific setting. In this case, there are two hospitals had the same instance of the EHR and therefore had more consistent data quality between these two. It's an important point, but they were able to analyze over 46 billion data elements and come up with quite robust risk prediction models using AI ML techniques and the collaboration between academics and Google. And I think this is a good model. However, I would also point out this is still just foundational evidence. These risk models aren't being used to improve the care and outcomes of patients yet. We still have the challenge of the clinical integration. Let me, in the last section of my talk here, shift to what we're trying to do with the American College of Cardiology and working in collaborations like this with AI Med. We know we can't do anything by ourselves, which I'll come back to in a second, but ACC Innovation Program is focused on the digital transformation of healthcare and the use of AI in the future of cardiovascular care. In 2017, we laid out a roadmap for innovation to try to take a stepwise approach to this. And I want to say I'm proud that we've been really busy. And what we've largely been busy doing is establishing the collaborations we're going to need, I think, to move this forward in a thoughtful, or at least I hope in a thoughtful manner, and look for more collaborations from this audience and others who are focused on this idea of augmented intelligence. We have a lot of strategic partners, including AI Med. These are all formalized in various ways in what we're working on projects. But I want to focus on the right side of the slide, which is we've made the commitment to actually work directly with tech companies, including co-development of the technology from start. And I don't have time to go through these, but I'm going to highlight two of them, just quick hitting here. Just as examples of what we're doing. So Maya is a remote monitoring platform. ACC helped co-start the company with Maya together with the inception of clinical use from the beginning, and it is now deployed in multiple healthcare systems in the US, taking care of post-acute patients and also hospital at home patients. And it's, a remote monitoring platform that is device agnostic. We can bring in and out the different biosensors. And what I want to focus on is not sort of the traditional EKG patch, blood pressure cuff, or weight scale, but rather we're starting to see the most interesting data from the wearable or non-wearable biosensors, such as a sleep monitor or ballistocardiograph. And this is very preliminary, unpublished data, but just to be illustrative that actually, even without any patient history, nothing from the EHR, in symptomatic heart failure patients over time, early models would suggest that change in sleep physiology is predictive of decompensation even before patients have started to retain fluid or gain weight on the scale. And then in imaging, of course, no surprise, for example, one of the companies we're working with called Clearly is AI interpretation of CT angiography, including the plaque composition. Is it necrotic versus calcified? And that in and of itself, the AI interprets very accurately and very rapidly compared to the manual annotation and so forth. However, the main reason we're interested is we wanted to think about a novel way to deliver primary prevention. Can we be better with the growing armamentarium of prevention medications to prevent heart attacks? And we're going to launch a prevention initiative in 2021 as part of this collaboration. So let me end with this concept of augmented intelligence, which I think is the future. What this computer needs is a physician. Great article by Abraham Verghese, Bob Harrington, Nigam Shah. And it's really this, that if we do this right, as I hand back to you, go back to you, Anthony, here, it isn't just artificial intelligence. It's artificial intelligence right from the beginning with clinical intelligence. And I do think if we go strongly after augmented intelligence and build the evidence, we can take this forward and we will evolve cardiovascular care. So thank you for your time. And Anthony, back over to you. I can't hear you yet, Anthony.
Yeah, no worries about my slides. We will post them and I will highlight my slides throughout the 5 hours we have together. So John, thanks for a wonderful introduction and to what's happening. I totally agree with you that we're following the footsteps of our radiology colleagues, and a lot of intensive effort is on imaging. But I think that, and I publicly said this, so I have to own it, that I actually think cardiology is one of the best, if not the best field to benefit entirely from the portfolio of tools that AI can offer. Because we have complex patient management, we have chronic diseases, we have imaging, we have decisions making in an ICU setting. We kind of have it all. And I think with just the tip of the iceberg, the low-hanging fruit in terms of benefiting AI. And I think probably no accident that we eventually met, because we're both in innovation and you have an interest in AI as well. I'm starting to think that the next phase of innovation projects in cardiology will have, at least in part, artificial intelligence or analytics involved, because that's sort of the next stage. What do you think about innovation and intelligence being intertwined now?
Yeah, I think your point's well taken. In talking about, well, I'll just cut to the chase and say I agree, and maybe we should jointly plan those, because we're at the place now where we have the right strategic and tech partners to be able to put these projects and move them forward. And to your point, I do think holistically imaging is coming quicker because it fits so well with what AI can do. But two caveats there. Number one, we really have to think broadly about imaging. Sometimes we just think of one imaging modality, but ECG, event monitors, a lot of the stuff we do are functionally images that can be assessed. And it's not just interpreting the image, it's also risk prediction off of the image. And then right behind that, and I think this is what you're saying, is cardiovascular care, imaging, sure, but right past that is a whole bunch of other things. What about biomarker data? Of course, omics. What about all wearable and non-wearable biosensor, voice, high optical imaging? All of that is high quality data. And so it has huge potential for application of AI or combinations of those modalities.
Yeah, that's exactly right. So I think, I think cardiologists can really embrace this technology by just thinking out of the image box and think about wearable technology, omics, think about your administrative tasks, right? So many administrative tasks would just, even something as mundane as pre-authorization for your catheterization really that takes so many human hours really ought to be automated. And I think we're just an amazing field as it is, but in terms of the future with artificial intelligence could be actually even more interesting. I'm actually predicting that more and more people will become interested in cardiology because we're going to take the most interesting parts and embrace the emerging technology. So I'm giving a talk later this week on the ethics of AI. And especially, I know you're, as one of the leaders at the ACC, is really dealing with that. And I always say, because I get asked often, how would I feel about the ethics of AI and in terms of using AI? And I always say, well, what if we look at it from the perspective of not using AI? How many cardiac patients are we losing because we're not thinking about artificial intelligence? And how do you feel about that sort of position that we're always thinking AI can lead to inadvertent deaths because of an algorithm? But I always think about the opposite situations, which is how many deaths are we losing? How many patients are we losing because we're not paying attention to preventable errors and preventable judgment lapses because we don't have an effective tool available?
Yeah, so I think what you just nicely outlined is you just brought back the concept essentially of design thinking. Because if we just walk into healthcare and say, we're just going to throw AI at whatever data set we can find, and we're blind to the potential for underlying data quality and algorithmic bias, sure as heck we will do it wrong. And there will be algorithmic bias, and that is scary. However, if you design from what problem we're trying to solve backwards, which is essentially what you're saying, and I strongly agree with, which is what problem or problems are we trying to solve, and how could AI help? Not just where's there data on which we could apply AI. It has to go the other way around. If we do the other way around, also phrased as what use cases might AI thrive in, I think we can reduce disparities and improve access to care, because AI can make us more efficient and extend access. So let me give very basic examples, because we've been talking with potential projects not only in the US, but in low and middle income countries, such as in West Africa, where they have huge challenges to access and to getting medications, and yet they have almost smartphone prevalence is higher than in the US. And there is the potential to show in very straightforward ways how to use digital health, how to use AI guided decision-making to augment their clinical communities and improve things like detection of valvular heart disease, improve hypertension management was a huge issue, stroke risk and so forth. And so there you're taking the problem and reverse engineering where the AI will augment us the best. I think in that case, it has all the potential in the world to reduce disparities, as long as that's the way we design it.
Yeah. Well, I'm just gonna, again, the slides will be posted, but this is just what I was talking about without my slides. I wonder if I had anything to do with how I voted, but the slide's not working. But this is how impressive AI is in predicting viral protein structures. Will be key for a cardiologist in the future if you think about all the medications and
drug discovery,
that we should start training our clinical colleagues to at least know the basics of AI so that we can better understand how we can apply all of this. And we just launched the American board, and here's the URL for those of you who are interested in a 2-day crash course and hopefully become more interested. Thanks to my ACC colleagues and friends who contributed to the book. Intelligence-Based Medicine is out now. I would encourage my cardiology colleagues to submit articles to the Intelligence-Based Medicine. It's a clinician-friendly AI clinical journal, and we just launched this year. I'll be reviewing my 98th manuscript since Q1 of this year, so it's been very impressive. And actually, Elsevier just gave me approval last week. So John, you'll be hearing from me about a artificial intelligence based cardiology textbook. So we're going to work on that for all of us. So, and again, here's the review course. We also have a society. Again, all these slides will be posted. I'm just want to show the excitement about convolutional neural network because we'll be talking about that throughout the day here. And it's basically filters and clever ways of mimicking the visual cortex to some degree. And it's just been a Cambrian explosion of CNN tools that are just really, really ripe for cardiology and medical image people to take advantage of. And this is recurrent neural network. We'll talk about that as a time series kind of deep learning that can be coupled with the CNN, the image one, to really give us, I think, future advances in interpreting echoes and 3D images. Natural language processing will be huge for us in cardiology, given the complexity of our diseases. GPT-3, if you haven't heard about it, is going to be a game changer. And robotic process automation for our administrative tasks. Edge computing, John talked about wearable devices. This is going to embed artificial intelligence into your wearable device. So you don't have to have all of the data go to the cloud. It'll just be taken care of locally. Think of it as a innovation of the AI for all of us. Just want to give tribute to my mentor, Dr. Norwood, who taught me about chaos theory. That's also going to be big in ICU medicine for cardiologists. And that's me visiting him earlier this year in New Mexico. And think about how we use our AI in the future. We need to think about cognitive elements, which will take advantage of our clinical wisdom. Imagine this is how heart surgeons can learn do heart surgery in the future.
It's best to make your incision right here.
This is not heart surgery, obviously, but
here is the front of the major fissure.
So anatomic structures can be identified with deep learning to guide particularly difficult cases.
The superior segment artery should be near there.
And just a few words about the FDA recent, since we last met, how they've been very flexible trying to encourage AI tools to be available. And also all the issues with bias we'll probably address later in terms of the degree of involvement of artificial intelligence. And basically the bottom line is we're sort of at this point. We're still estimating capabilities, but I think 10 years from now, 2030, when we talk about AI in cardiology, first of all, we probably won't be talking about AI in cardiology because everything would just be part of cardiology. But I think we're still underestimating what we can do in the 10-year period. Put a little plug in for the ACC there. I don't know if you saw that flag. Okay, so as with the pandemic, I think AI in cardiology is summarized by Winston Churchill's words. Now, this is not the end. It's not even the beginning of the end. It is perhaps the end of the beginning. So I think it's an exciting time. My daughters in Laguna Beach want to say hi to all of you and want to thank my donor and my program at Children's Hospital of Orange County. And there's my contact information. So I think it's an exciting time. And if those of you who are a little bit daunted by the complexity of AI, just think we're cardiologists. We went through training that is equally as hard to our data scientist colleagues just to understand all the nuances of cardiology and cardiovascular physiology. So it is definitely doable. So with that, John, again, thank you for your partnership with this meeting. I'm going to have you introduce our speakers for the next session. Thanks, John.
Thank you, Anthony. Really terrific, and agree with all your concepts. So we're going to pivot right into this, into the topic of data and databases in AI and cardiology, which really does have to be the lead topic. And I'm really honored to have two great speakers here today with us. And I'm going to start with Dr. Louise Sun, who is the Director of Big Data and Health Informatics Research at the University of Ottawa Health Institute. And Louise is going to speak to us about a critical look at big data for medical AI research. Then we'll pivot, and we're actually going to come back to Louise a little bit later in the session. So Louise, let me hand off to you and welcome.
Thank you, John. And I'd like to thank Anthony and Alexis for inviting me back. So I'd like to talk about critical look at big data. Oh, sure. So let me try again. Is that still the speaker view? Display settings.
I think if you just go under slideshow and start, then you'll be fine. There you go.
Okay, there we are. All right. Okay, so and so I'd like to talk about how to critically look at big data for medical AI research. And we know that information is key for better patient management and resource allocation in healthcare. And data is the basic building block of that information that we really need. So so today I'd like to go over briefly what big data is, how data is used in machine learning applications in medicine, and how to harness data to its fullest potential. So what is big data? We can start with a very boring definition from the Merriam-Webster dictionary, in that data is information in digital form that can be transmitted or processed. And big data is just really data that's so large that it's unmanageable by conventional means. So what that means for us in terms of processing big data is that the process of extracting data, validating, storing that data, transferring, access, sharing, and eventually we're talking about ownership of the data, privacy issues, as well as analytics and how to disseminate our findings. So traditionally, big data is defined by the 3 V's, and afterwards, many other V's have popped up in terms of defining it. So the traditional 3 are volume of the data, velocity at which it accumulates, and the variety of data that's available in our repositories. So some of the types of data that we commonly encounter in healthcare are administrative. There are clinical registries of various kinds. There's EHR data. There's Texas data, imaging data, as well as the various types of omics data. So there's genomics, epigenomics, proteomics, metabolomics, and many others. So one example of an integrated source of big data is the Institute for Clinical Evaluative Sciences, or ICES in Ontario. And so basically, Ontario is the largest province in Canada. 40% of the Canadian population lives here. And we have a universal one-tier publicly funded healthcare system, which means that from the moment someone enters or is born in the province till the moment they die or leave the province, we have complete longitudinal healthcare data on all of those patients. So there's no issue of selection bias or loss to follow up here. So we have administrative data, which is, it encompasses ambulatory and inpatient encounters, procedures, medications, and outcomes. There's clinical registries of various kinds. So for us, the most important one is cardiac patients in terms of all sorts of procedures they undergo and procedure and patient level details, as well as registries on cancer and stroke. We have some EHR data as well pertaining to laboratory values and some of the imaging information. So some of the applications of data in medical AI, especially in our field, are first of all visualization. And this is the basic step that enables us to learn about what's in our data, what's the pattern of that data, and basically what we can do with it. Predictive analytics has gained a lot of traction, and basically what it can be used in doing is, number one, to provide clinical decision support in terms of helping us making better diagnosis and to better personalize our treatment to each patient. And we will give you a demo of a predictive analytic tool that we developed to help triaging patients during the COVID era a little later on. It can also help out with administrative tasks. So it can help with better resource allocation and better planning of our clinical operations and of our resources. So drug and biomarker discovery is another application of data in AI. And we can also use AI and data to predict user behaviors and to to enhance our ability to communicate with our patients. And another application will be in medical imaging. So some of the common dissemination methods are apps, wearable technology, and EHR integration to provide automated decision support for clinicians. So in working with EHR data, here are some of the things that I have learned that I thought might be important to share. So first of all, it's very nice to be handed over a platter containing various amounts of data on it. But I would advise that we always go the extra mile when before we even start the project and before we start to use that data. So first of all, we need to learn where the data comes from. You know, who collects it? Is it a clerk? Is it an inexperienced medical student? Versus a more experienced clinician who's routinely collecting it according to standardized definitions. Was the data extracted manually versus was it extracted from an automated process? What's the frequency of the extraction? What devices are involved in collecting and transmitting the data? And what are the variations in the patterns of that data? And is this variation normal? So that requires the integration between clinical acumen and also some knowledge in IT and data science. So we need to know how the data is extracted. So by whom, where the data comes from, you know, which database it comes from versus if it's from the same repository, what part and when was the data extracted? Was there an algorithm that was used, and what's the validity of the algorithm, and what's the validity of each of the data points that we're getting? So second of all, question what's in front of you. In my earlier days, I used to think that more is better, but now I kind of am shifting my frame of mind around that. So sometimes a lot of data doesn't just impose on processing power, but it could also introduce some extra noise into the data set. Is the data you have analysis ready? So if we're talking about EHR data, then the answer likely is no. We need validated methods for capturing and extracting data, and different validation methodologies are required for different types of data. If you're talking about biometric data versus demographic data, for instance, we need to be able to separate the forest from the trees, and we need to first synthesize data into usable information before we can apply that information into the projects and into the machine learning methodologies that we wish to employ. We need to know the caveats in the data set and how to deal with them. So missing this is a common thing that we face. And sometimes just because the data is not picked up or seems to be missing, it doesn't mean it's not there. It doesn't mean it's not existent in your repository in a different form. So how to find surrogates that are valid for the data, how to make your filler up for the missingness interoperable from center to center, and is the missingness truly at random, and how to deal with redundant and conflicting elements in the data. And I believe Dr. Window will talk about some of those points in more detail in his talk. So why should we care? Well, data quality directly impacts on the performance of the model, and the initial model might seem to be very optimistic in its performance, but that could be because our data set is not as good as it could be. And when you try to apply that model in a different setting, you'll find out that it lacks generalizability. It actually doesn't work really well in real life in a different place. And so bad data is eventually really just leads to ineffective modeling. So that's my synopsis. Dr. Window will next go in to talk about a real life case to show how some of those principles are applicable. And I will then come back and provide a demo on the data-driven app that our group has developed. Thank you.
Thank you, Louise, and fantastic talk. we'll pivot right in, as you said, to Dr. John Windle. John is a longtime friend and colleague of mine, and really a thought leader in applied informatics, I like to say, actually applying it in care. John's a professor of internal medicine in the Holland Distinguished Chair in Cardiovascular Sciences at the University of Nebraska Medical Center, and very involved in national efforts in the U.S. American College of Cardiology. And so, John, I will hand off to you at this point.
So hopefully I will share the right screen with you. Please let me know if this is working for our folks.
It says good data. Except for we're in your notes presentation again.
Okay. Yeah. That's what I was concerned about. Let me. Just a second here. It gave me a view I'd never seen before. There we go. Now are we to the right screen? Okay. Now? Good. Well, thank you very much, Anthony and John, for having the ability to present at this conference. I've been very interested in clinical informatics and the electronic health record for quite some time, and more recently in the role of artificial intelligence. And as we look at this, the thing that I'm going to talk about, advance to the next slide, it is something I had the ability to work on in terms of the American College of Cardiology and American Heart Association performance measures. And it was an interesting use to sit down and think about performance measures, how many clinicians are evaluated with the simplest of all tools, the measurement of a blood pressure. And I thought this was the simplest use case until I started digging down with it. And so as we see in the guidelines, we have definitions for normal blood pressure, pre-hypertension or elevated blood pressure, stage 1, and stage 2 hypertension. So we looked at that and said, okay, how do we get that into place? Well, the first thing we start to notice is the performance measures now has given us measurements in clinic, measurements at home, and ambulatory measurements to put in place. So what we did is then, and I don't expect you to read all of this, is break down the performance measure into the field code representation and values of each of those sets. And to show you in a little larger view, what sort of standards were we going to use? So the definition of systolic, we used LOINC codes with the representation. Clinical blood pressure, there's a special LOINC code to look at there. Home blood pressure is ambulatory, and figuring out the diagnosis of hypertension and exclusions. So the first thing we needed to do was map the guidelines and the performance measures into a computable phenotype. One of the things that was noticed is that according to the guidelines, you should measure blood pressures twice using careful readings and do it on 2 occasions before you make the definition. Much of this, and for non-clinicians, this may not mean much, but the SPRINT trial was a hypertension trial that had a major impact on our management of hypertension. In the SPRINT trial, they actually used 3 blood pressure measurements at 5 minutes intervals and then averaged them to come up with the workable blood pressure. So we took a look at our data sets, and as you can see, we have nearly 5 million blood pressure recordings in our process. What we saw in our outpatient clinic visits, though, is in only about 17% is there actual evidence of 2 blood pressures taken in one occurrence. So now we start to understand and get to dissect some of the problems with translating guidelines and performance measures into clinical care. Next, we looked at blood pressure status. And this seems kind of a simple thing, but it was really a learning experience for me. Again, if we take the nearly 5 million patients, you can see in the green, 1.6 million had normal blood pressure. Nearly 800,000 had elevated. But amazingly to me, in looking at this, a scary number, 1.6 million had stage 1 hypertension at the time of their clinic visits. So as we're starting to dissect, I said, well, what if you take and look at an individual patient? Does this help us? And this is the blood pressure measurements that we have in our system from a single patient. The blue is their systolic blood pressure. This kind of orange is their diastolic blood pressure. And what you see is there are values that are sometimes less than 120, a number that are in the middle range of the pre-hypertension or stage 1, and then most in the stage 2. And that's shown in this slide. So even within an individual, you can be normotensive, elevated stage 1 or stage 2 hypertension. And this actually presents a clinical challenge as we go forward of what actually constitutes hypertension. So what I look at in this is we need to do this sort of detail before we can break it down. And as Dr. Rumsfeld talked about, there is the concept of garbage in or garbage out, is the concept of flawed or nonsense input data, or for our UK colleagues, rubbish in or rubbish out. And good data requires the discipline from the very beginning. It requires a dialogue between the guideline and performance measure experts and the clinical informaticists. My thanks to our research team of Stephen Scott, who's associate professor in AI, and my graduate students, Eve Shamavu, Garrett Workey, and Rinal Wolok, and my colleague, Tom Windle. So in conclusion, as pointed out, deep learning from the EHR is a little like trying to reconstruct an elegant meal from what is found in the garbage can. What we look at and what I want to promote is that good AI, like good cooking, starts with good ingredients that are very well defined and known. With that, I'll stop and see what sort of questions that may develop over the period. Thank you very much.
Thank you, John, and again, Louise, just fantastic stuff, and it begs a ton of questions about next steps. We have a little bit of time, but before we do have some questions coming up in the chat as well, but we wanted to, this is orchestrated as the next step, jump back over to Louise, to show us, or at least point us towards a tool that has been developed. And that was the next question. What have you developed in tools? So this is great.
Great. And so this is the link to the tool. It does require a sign up, but it is free and open for everyone to use. I'm not sure, John, if we have time to do a 2-minute demo, or should we just jump over to questions and answers?
I think we have time for the demo. I think people would be interested in seeing an applied tool based on the chat and the questions we're getting.
Sure, that sounds good. So can you see my screen with the web page? So this is a sign-in page, and so basically you need to create an account to log in. And at the upper left corner of the page, it gives you a choice of which risk calculators to choose. And so a bit of background on this is that we know that COVID has introduced quite a bit of problems for cardiovascular patients in that the wait times have been prolonged for cardiac procedures. And the cost of that, unfortunately, is an increasing amount of morbidity and mortality, even in patients who are waiting for their life-saving cardiac procedures. And so we developed a tool to look at which patients are at the highest risk of death and unwanted complications while waiting for surgery, so we could prioritize those patients for earlier surgery. And at the same time, we're keeping in mind that these patients are also competing for precious ICU resources with COVID-19 infected patients who are needing ventilators. And so we have developed a method of estimating which patients will be high resource users and which patients will be low resource users in terms of their ICU length of stay after their cardiac procedures. And so I wanted to show you, so basically the top one, the Cardiology 1.0, is the pure ICU length of stay score. But the 2.1, which is the COVID triage tool, is an integrated tool that estimates the likelihood of a short ICU stay, less than or equal to 2 days, prolonged ICU stay, 7 days or more, and their risk of death while awaiting surgery. So just scrolling down here, and so it's basically like a MedCalc type of calculator. So if we're making up a patient here, and you see on the right-hand side of the page, you start to get a summary input. And this is us making up patient characteristics. You have class 3 angina. You don't have heart failure symptoms. You have preserved ejection fraction, hypertension. You're starting to see that the risks are starting to change in response to our input. So if you also have severe aortic stenosis, and say your creatinine is this, you have a history of psychosis, that actually dramatically increases your risk of death while you're awaiting surgery. Your planned surgery type versus complex, which is a combination of CABG and valve. And let's say the operative status priority is deemed to be urgent, and we can provide definitions for these priority settings. And so we are actually in the process of improving the user experience by adding some decision support phrases here. So for instance, the probability of death on wait list of 0.24% or greater is actually considered the cutoff. And so the negative predictive value at a risk of death of 0.24% is 99.9. And so if your risk is lower than 0.24, then surgery doesn't need to be done right away. And we're fairly comfortable with that cutoff. Whereas if the risk is any higher than that, then this patient needs to be prioritized more than the others. And this is your predictive risk of short versus long stay here. And so our institution has been using this for the past 6 or 7 months. And I'm happy to report that we've been able to shift our OR scheduling on a daily basis according to it, in that we're able to schedule the long stay patients towards the end of the week so they could recover in the ICU over the weekend. We've been able to perform a higher number of cardiac surgery cases than the rest of the province because of it. And we've ran into less instances of case cancellations, and we've just been able to be a little more efficient from this data-driven tool. So just wanted to be able to share, and the link is cardioottawa.ottawaheart.ca.
Okay, thank you so much. It's this idea of demonstrating an applied tool that's actually being used in clinical setting, I think is sort of the bridge that we needed to cross. So thank you very much for that. We do have a question, and a couple questions have come in, and I'm going to merge them together. And John, let me aim this at you because it's right up your alley, which is, you know, I think we're seeing as guidelines and expert consensus, clinical decision pathways or other things are becoming more nuanced. They're becoming more complex. We have more classes of medications to use. I think one of the questions is, the question that chat was more literally, is it even reasonable to expect clinicians to know all this and keep up with everything, not to mention the medical literature? I think we know the answer to that is it's not no one person can. But how do you see potentially, given the sort of challenges you laid out, AI helping us with that kind of sort of access to knowledge, actionable knowledge when you need it?
Thank you. For us, the direction we're heading is towards what is called collaborative artificial intelligence, more based on knowledge base than deep learning per se. So as we look at this data, what we see at first blush is that our computer systems or AI do much better than clinicians. But we really believe to have true actionable items, it's got to be the clinician plus the AI. And so it goes back to what you were addressing before. I think when we set up the guidelines, we need to work on good clinical informatics so we have good data at the front end, and we have a clear understanding, for instance, how do you apply the sprint data practically to the clinical setting? So very few patients are going to have 3 blood pressure checked at 5 minutes intervals in a busy clinic. So what's the real world evidence that we need to get to, and how do we get there? So I think that's where the future is.
And let me follow on in that and ask both of you this question. So John, you're on, I'll ask you first, and then we'll pivot to Louise to the same thing, because I think it's fair, is our tradition is to quote unquote keep up with the medical literature and then memorize or understand the guidelines or other clinical guidance as it comes out. Is it realistic that maybe we will shift instead to knowing which AI or machine learning algorithmic tools will help us apply the guidelines and practice in the EHR? Can we reach a point where, as guidelines come out, then they're applied as tools in the EHR, still keeping the clinician in the loop for sure, but maybe we start to focus more on which algorithms are helpful rather than which guideline? That's sort of the question in the chat. John, how do you react to that? And then we'll go to Louise.
From my perspective and from our research, what is really necessary is intelligent agents. And what we see in our research is, think about it practically, a medical student is going to want and need different data than a resident, than a fellow, than a practicing attending. And so one of the things we found in our EHR research is senior experienced clinicians can look at a massively amount of data very quickly and assess. So for them, the gap that they're looking for is really different than the gap that a fellow is looking for. So what I'm thinking about is how do we identify the gaps and develop tools to help that individual clinician.
That's great. And Louise, where do you stand on this? It's a different type of tool than the one you just showed us. That this idea can't, but maybe it's in your pipeline. I don't know. Is tools, AI tools, to help really bring sort of current guidelines to practice in a different way.
Right. So that's a very interesting question, John. And, in addition to the other John's excellent points, I was wondering if, every time a new clinical practice guideline comes out, can it come out at the same time with an app or with an AI application with it so that we could point to it? So every time, we talk about a guideline, a concurrently published app could be used as a reference on how to apply it. And if that is the case, then can those apps just be integrated as decision support tools into the EHR system so we don't have to memorize, what's the right app to use? Because there's going to be different brands of things, and there's going to be validated versions versus some of the less validated versions. So I think instead of memorizing, can they just kind of automatically be tied to something that can be applied?
Yeah, so you went right down an alley that I think is the right alley for the three of us towards the end of this session. We have a couple of minutes here because it's going to loop back to both of your talks. So what John just said and what you just suggested, can that be done? Could, for example, our medical professional organizations like the ACC take a role in, as the guidelines come out, also having the algorithmic applications that you would need to integrate it into clinical workflow? Can that happen? Absolutely. But what are the barriers to that in application in clinical practice? There's something in the chat about, are the EHR vendors going to take on updating these algorithms? I don't know how you both feel about that. That sounds like a terrible idea to me. I think the clinicians, researchers, our professional organizations and we as professionals can and should guide that. But we're going to quickly run against two problems I'd like to have each of you comment on, Louise, and then back to John. The first is APIs, to have an application programming interface, if we make this elegant thing to go with the guideline. But right now, most of the electronic health records, at least in use in the United States, are not very warm to allowing those APIs to be applied. I mean, that would be ideal if it came out across the system and globally to use these, and that's what the chat is saying. But I feel like there's a block there right now in practicality of that API actually getting in, say to the Ottawa Heart Institute. And then the second thing is the tough one, is back to data for both of you, which is, it's one thing for you to be able to apply it or develop the tool you nicely show you've developed and deployed, Louise. But I don't know if that same tool could be deployed at the University of Colorado Hospital where I work, because of this is interoperability. I try not to avoid the word because people kind of sink when they hear it. But if we don't have consistent data or interoperability for these APIs or for the data consistency, is this really going to work?
Yeah, so great questions. So I hope I remember the first question correctly. In that, I
think it's whether if we have an API, are we even going to be able to use it in our own EHR? Is it not? We could create it, sure, but are we going to be able to use it? And then the data interoperability.
Yeah, agreed. And I think with the systems, and I hate to mention names, but for systems such as Epic, I'm not sure if we're quite at the age where APIs is possible. It would be great to have it, and I think it would introduce a lot of wider applications of a lot of the useful apps. But unfortunately, I'm not sure if we're quite at that stage yet. And to talk about applicability of a tool such as the one that we demoed earlier to another center. So I'm happy to report that the data sources we used were very representative populations, and in that I mean one of the tools was derived using University of Ottawa Heart Institute data, but we validated it across the province of Ontario. And so Ontario is a very representative, very ethnically diverse province. And so I validated well. And the other tool was actually derived directly on the Ontario data set. So we had a high quality clinical registry with all the triaging information in addition to other clinical information that's been validated. So we're quite confident that it'll work well. But your point is well taken that the data source from which those tools are derived, it really plays an important role on how applicable those things ultimately will be. And sometimes you have to train this this stuff in different places where you bring it over to. So.
Yeah, so as I transition back to you, John, and you'll get the final comment here, we have enough time, is Louise did hit on a couple of things that I think you just have to say the words, which are, you didn't just derive and do an internal validation at a single center, you did take it and do additional validation, at least in the province, and that the underlying data set is on representative patients. Those two things are so important to avoid algorithmic bias and have the chance at generalizability or getting it into other settings. It still belies the issue of whether or not we can get APIs into Epic or other systems, and it still belies the underlying data problem. So John, back to you, since you and I work closely with the ACC and other similar organizations, if we evolved in a place with guidelines and clinical guidance, that at the same time we also provided the applied, not just apps, but the actual way you might apply them through application programming interfaces into workflow. Right now, I remain skeptical for the reasons Louise alluded to. It's not just Epic, that it's also the heterogeneity of our system, that those could be picked up and utilized. But I'd love your thought on the API issue, but even more so, what do we do about the data variability between and even within centers, inpatient, outpatient, with our ability to develop and deploy meaningful AI tools?
I'm going to be a little more optimistic. First off, to answer the question, EHR vendors are definitely the wrong people to be developing this. And it really is specialty societies, and that's how we push data forward. I would say also on the optimistic side, I listened to a lecture by Don Rucker, the head of ONC in the US. And he is actively working on breaking down the barriers. He believes APIs are the right answer. You're going to hear the word FHIR standards all the time. There are problems within FHIR itself, which is it's just a pipeline. It doesn't really coordinate what data comes through. But I think by specialty societies and clinical informatics people getting together at the front end, we can actually do this. It is a finite number of things that can be done. And in our previous research with AHRQ, we actually found that cardiovascular medicine is practiced the same, independent of whether you're academic or private, West Coast, East Coast, or the Midwest. And therefore, we can develop generalizable solutions.
John, not only was that it was optimistic, but realistic and powerful. That I do share very much that vision of a roadmap. And you also are perfect in your timing, true pro. We are right at the end of the session. Please, we can't do the usual round of applause virtually, but I hope you all appreciate the depth of expertise and knowledge that Louise and John just shared with us. Thank you all for your time. And we now have a 10-minute comfort break. So please take a 10-minute break and then we will rejoin the meeting and it'll come back. Anthony will rejoin us in 10 minutes. Thank you all.
Welcome back, everybody. What an amazing first module on data. And thank you, John and Louise, for an outstanding session. I can tell from the chat area, the questions are just streaming in very fast, but we'll try to save the chat for you. So, and have the speakers try to answer some of those questions. So I think during this pandemic, one of the things I missed the most is to rekindle friendships with special people I've met on my 10-year journey in AI medicine. And one of the people I really thought very highly of is Rob Brisk, who's going to moderate the session. And he's a true clinician data scientist, which there aren't too many of, and working really hard on machine and deep learning. So Rob, I miss seeing you in person, but it's good to have you virtually. So Rob?
Likewise, thanks, Anthony. Great, well, really excited to be introducing this session, which is on machine learning and deep learning. We're going to be hearing about the use of CNNs in the care of patients who have had a repair of the tetralogy of Fallot. So pediatric cardiology, we're going to be hearing about machine learning for ECG analysis and also machine learned decision trees for cardiovascular risk prediction models. So 3 big applications of AI in cardiology coming up from 3 fantastic speakers. What I'll do, I'll introduce them one at a time, each one before they speak, as much as anything to let them know when they're supposed to come on camera in this new post-COVID world. So our first speaker is Dr. Ashu Tandon, who is a pediatric cardiologist at UT Southwestern, and he's going to be speaking to us about tetralogy of Fallot and CNN. So welcome, Ashu. I'm going to disappear here and let you take it away, and I'll pop back in towards the end of your talk.
Okay, thank you, Dr. Chang and Dr. Rumsfeld and Dr. Brisk and team for letting us talk about our work here. Obviously, this is a team effort. I just get to talk about it today. As was mentioned, we are going to talk about machine learning to automate ventricular contouring in congenital heart disease with tetralogy of Fallot as our example. These are the disclosures. And just to be obvious about it, we did this project with Circle Cardiovascular Imaging, so their name will come up. So what's cardiac MRI? It's an MRI for your heart. And I mean, I probably don't need to tell that to a room full of people interested in cardiology. But it is the gold standard for measuring ventricular volumes, especially for the right ventricle. And it's one of the better ways of showing 3D anatomy. And, to get these values, basically you need to outline the endocardial and epicardial surfaces of the ventricles. So basically going from this raw image to this contoured image where you see the circles. And then the software adds up the size of these contours and gives you ejection fraction and volume. Contouring. So it takes about 20 minutes to contour a structurally normal heart. For congenital heart disease, we know that it takes even more. And then automating would improve the workflow for clinical CMR and CT and echo, which we'll hear about as well. These are some of the limitations of contouring, including reducing intra-observer variability, and it's just really boring. So automating that would help. Doing CMR in congenital heart disease is especially important because we use these values to make clinical decisions about our patients, like when they should get a new pulmonary valve. And in our study, we used repaired tetralogy of Fallot, which is the most common indication for CMR in congenital heart disease, because CMR is the gold standard for RV volumetrics. And in this disease, the RV is often more affected than the LV. So there are automated methods that already exist, mostly for the LV and some for the RV. They use atlases and motion-based methods, and there are deep learning methods for the RV. There are other CNNs for adult CMR that have been published, and then there are iterative methods for congenital heart disease. And then obviously there are commercial methods, and multiple companies have used CNNs to do this contouring, though not many have actually published the underlying data, though there must be some because they're FDA cleared. So our approach was to use a CNN already trained for mostly structurally normal hearts to see how well it works in congenital heart disease and see if we could improve it. And we purposely teamed with a commercial partner to bring the results of clinical practice faster. So the study was in 2 parts. This first part, we trained on mostly structurally normal, or MSN hearts, and we tested it on repaired tetralogy of Fallot. So here's an example of the 2D contours generated by humans on the left and the mostly structurally normal algorithm on the right. And then you can see below how they're interpolated into the 3D shapes used to calculate volumes. And what we found, which we thought was pretty obvious, but hadn't really been shown that much before, is that the contouring was worse for the RV than the LV in tetralogy of Fallot. And that's probably because the RV is more misshapen in tetralogy of Fallot than the LV is. And we use both spatial metrics like Hausdorff distance and volumetrics like EF and diastolic volume measurements. So then in the second part, we actually added tetralogy of Fallot data sets to the 5,000 mostly structurally normal hearts that were used to train the algorithm. We took 57 tetralogy of Fallot patients, put that in there, and then we tested it on a 30 case testing data set. So there were no significant differences in patient characteristics between the training and testing data set in terms of age and BSA and heart rate. And here's an example of this improved algorithm and what its contours look like. And what we saw was that specifically for the RV endocardium, this new algorithm had improved spatial characteristics like Dice coefficient and Hausdorff distance. And then also correlation to volumetrics like end diastolic volume, and it had improved correlation, decreased bias, and decreased percent error. But what was also interesting is where did the algorithm go wrong, right? And so you can see that here's a set of 2D sections, and these arrows point to slices where the RV is dilated and kind of comes above the tricuspid valve plane, and you can see that the algorithm contoured up into the atrium and didn't recognize that that was not just ventricle. And so this problem of, and then it also extended past the apex. And part of that we think is because the UK Biobank, which was the training data set, was almost always restricted just from apex to base of the LV. But the RV in tetralogy of Fallot goes above that spot. It goes above the tricuspid valve plane. And so, you know, it was trying to recognize things that it had never been trained on. And so, you know, this was part of why it did get better, but there were still significant errors here. So, you know, unexpectedly, we found that the LV is better than the neural network was better for LV contouring than RV contouring. And it did improve, the retraining the algorithm with tetralogy data did improve contouring for most contours on spatial metrics and the RV for volumetrics. So we agree with using both of those tools, and we found some of the sources of error. And one of the things I'm proud of is that this is already in clinical use. So these new training data went into the commercial algorithm and made it better for everybody to use. But you know, that's, and you know, compared to some of the adult studies, maybe this is, you know, 10 years behind, which is common in pediatric cardiology. But you know, I think what's next was what was most exciting, right? So it opens up the possibility of more in-depth understanding of cardiac mechanics if we're able to look at each slice and contour it. We're lazy and we don't have time, so we just do end-diastole and end-systole because that's how much time we have. But if we can automate it and make it faster, maybe we could learn more about mechanics by understanding the shape throughout the cardiac cycle. You know, and then as a community, I think this tells us we need to collate our data so big data approaches become more meaningful and easier to implement. And it would be nice to see some of the data for commercial partners as well, because it might help us fix what's wrong. And so how do we solve the problem of numbers in our field? Should we add congenital cases to normal cases, which is what we did? Should we think about transfer learning, federated learning? I'm sure these kinds of things are coming in the future. And so, our goal is not only just to improve the workflow, but then derive new imaging-based biomarkers out of those data that already exist. And we're using voxelmorph and other types of tools like that applied to these data to understand new biomarkers of disease in patients with repaired congenital heart disease. So I wanted to thank our lab and the team at Circle.
That's brilliant, Ashu. Thank you. That was a fantastic talk. What I will do, I will hold off questions for now, and we'll do all the talks. I gave a very short introduction for the same reason, because I want to leave a bit of time for discussion later. So I'll just introduce the next speaker and then the speaker after that, and then we'll come back to you and do the questions. Is that okay?
Sounds great.
I'm sure there will be plenty, and I have a few. That was a really good talk. Thank you very much. Right, well, as I said, we'll move swiftly on to the next one and come back to discussion later. So the next speaker is Dr. Lopez Jimenez. I'm hopefully pronouncing that right. I actually had to ask my Spanish brother-in-law to record a pronunciation for me. So Dr. Lopez Jimenez is a professor of medicine at the Mayo College of Medicine and co-director of AI in cardiology at the Mayo Clinic. And going to be speaking about machine learning for ECG analysis, which is my research field. So in that world, some of the papers that Dr. Lopez Jimenez and the team have produced in the last couple of years have been the real big hitters. So I'm really excited to hear about this. And I can guarantee you I'll have some questions at the end of yours as well. But for now, I'll disappear off screen and let you take it away.
Good, thank you. Well, thank you for the invitation, and it is my pleasure to be here. And I will just go straight to the presentation so we can save the time. The only disclosure I have is that we have licensed the technology to detect low EF to ECO, which is a company that manufactures electronic stethoscopes. The electrocardiogram, as most of you know, is a pretty old technology. It was invented in 1895, and it hasn't actually changed much. Everything remains very similar to what it was from the very beginning, including the way the report is, the printout of the electrocardiogram comes out of the machine. Very similar technology. And it has been traditionally used to diagnose a number of cardiac problems, conditions, myocardial infarction in particular, arrhythmias, hypertrophy, and also as a measure of the risk for sudden death. So thinking about using AI to enhance the interpretation of ECG, certainly there is a lot of potential to use AI to make the interpretation of ECG automatically in a way to create a first pass interpretation, something that right now computers are doing that already. And anybody with a good ECG machine will see that the printout comes with a series of diagnoses that the computer generates. It is something that has been helping different areas in the world with no professionals able to diagnose things, to have a fairly good and accurate diagnosis. But what I will present you right now is different. It is trying to detect things that go beyond what the ECG was intended to diagnose from the very beginning, and also to diagnose or to see things that the human eye cannot see. This, we believe, provides a lot of value added, and will go beyond the standard definition of just normal or abnormal. I will present you with three algorithms that we have created. In all of those algorithms, we use convolutional neural networks, and I will not get into the details in how those networks work, just to highlight the fact that by doing this in this particular way, we don't have explicit rules during the machine learning process, and give the machine the freedom to discover and identify new things by playing around with all these convolutional layers of data. The first one I will show you is a algorithm to diagnose hypertrophic cardiomyopathy. As you probably know, this is the most common diagnosis in people who play sports and die during a sport, particularly people younger than 40 years of age. So it's a terrible condition to have, and it's difficult to diagnose in the masses because it generally requires doing an echocardiogram, advanced testing, etc. So it is critical to have simple and accessible tools to screen the population for this condition. That is a deadly condition for those who have it, and many of those might have this in an asymptomatic state. So to do this, we selected 3,000 patients with hypertrophic cardiomyopathy and about 60,000 controls. We created 3 different sets, the training set, the validation, and the testing set. And the results were actually extremely good, with an area under the curve of 0.97. And the testing area under the curve was very remarkably similar, 0.96. As you know, we rarely see areas under the curve that are that close to the unit. So an extraordinary accuracy to detect hypertrophic cardiomyopathy. Now, let me show you one example in how this might represent the new era for ECG as we use AI and machine learning repurposing this tool. This particular case, a 25-year-old woman, you can see this electrocardiogram that is completely normal. I mean, if anything, you will see some non-specific ST abnormalities in B1, B2. Other than this, it was actually a completely normal electrocardiogram. This patient came to Mayo Clinic because she had been diagnosed with hypertrophic cardiomyopathy before. So when we tested the algorithm on her, it shows a 72% probability to have hypertrophic cardiomyopathy. So obviously in this particular case, we knew that she had hypertrophic cardiomyopathy, and she actually had a surgery that has the purpose to release the obstruction of the outflow that these patients have. It's called septal myectomy. For those who are not familiar with this surgery, essentially the thick wall that is obstructing the flow of blood, the surgeons take a chunk of it to release the obstruction. And see how a few days after she underwent the surgery, the ECG became more abnormal. You can see significant abnormalities by all means. However, the algorithm show a very low probability to have hypertrophic cardiomyopathy. Very interesting finding. The next algorithm I want to describe is the algorithm we created to detect atrial fibrillation when the electrocardiogram shows normal sinus rhythm. Atrial fibrillation, when it's paroxysmal, is very difficult to diagnose, especially because it presents for few minutes at a time, every several days, every several weeks, or even every several months. So occurs very rarely, but when it happens, it increases the risk for a stroke. Most times when it's paroxysmal, it's actually asymptomatic. So it's very difficult to recognize when the patient is having this. And the problem is that in a number of patients with paroxysmal atrial fibrillation, the very first manifestation will be stroke. So there is an urgent need to identify those patients early on time, but right now it is not that simple. So to find the way to diagnose atrial fibrillation when the electrocardiogram shows no atrial fibrillation, we use more than 1 million electrocardiograms in more than 210,000 patients and created 3 different data sets in a total of almost 170,000 individuals. With this algorithm created through neural networks, the diagnostic accuracy was 0.87 for the arrows for the area under the curve. Now, when we use more than 1 electrocardiogram to create the output, the accuracy actually went up with an area under the curve of 0.990, with sensitivity and specificities above 80%. So fairly good sensitivity and specificity for a screening tool like this. Now, let me show you this very interesting case. What you can see in those dots, blue dots represent electrocardiograms that were below the threshold for being labeled as high risk for paroxysmal atrial fibrillation. And the risk is represented in the y-axis. Red dots are electrocardiograms above the threshold or labeled as positive for high risk for paroxysmal atrial fibrillation, which shows a probability of 10% to create the label of positive or negative. So this patient started having several electrocardiograms in 2003 and beyond that were labeled as positive for paroxysmal atrial fibrillation. The patient presented with a stroke in about 2014, but the ECG was still in sinus rhythm. Had a second stroke in 2020, and that's exactly the time when the first electrocardiogram was reported with atrial fibrillation. So the question is, would we have prevented the first stroke and obviously the second stroke if something would have been done here when the patient had been identified as high risk for atrial fibrillation way before, years before the first stroke occurred? I think that's a very interesting question we need to answer in the next few years. And see how the electrocardiogram was completely normal. Nothing here will suggest anything that will make you believe that the patient has had an increased risk for atrial fibrillation. Now, the last algorithm I want to present is the one that probably many of you have seen around. We have been talking about this for more than a year. And this was an algorithm to detect low left ventricular ejection fraction, or low EF for short. We also use convolutional neural networks to create this. And as you can see, the accuracy was actually pretty good when area under the curve of 0.93 in both the validation and the testing. In this particular case, that was interpreted as a completely normal electrocardiogram, comes from a patient that was 35 years of age whose sister died suddenly. In this particular individual, the ECG reported a probability of 76% for having low ejection fraction. The echocardiogram, sure enough, demonstrated that the ejection fraction was significantly reduced, even though the electrocardiogram was seemingly normal. Now, this is a different case, and this is the last case I present, that was labeled as positive for low EF. But guess what? The ejection fraction was not decreased. It was kind of borderline, 50%. So it was officially labeled as a false positive ECG. However, we did a particular subgroup analysis following individuals that were labeled as false positives over time and see how those that were labeled as positive, according to this algorithm, had an increased probability to develop a low EF over time. In this particular case, that the ECG was normal but labeled as positive and the ejection fraction was not low, 5 years later, the ejection fraction came down to 31%. So the question is, was this truly a false positive? We believe that the electrocardiogram, once it is labeled as low EF, is representing either a low EF or a high probability to develop low ejection fraction over time, perhaps detecting things that not even the echocardiogram is able to detect. So in summary, we believe that the electrocardiogram can be used in many different ways using AI and machine learning, and will be able to identify things that the human eye cannot see. We don't know how it works, and as you know, this is one of those classic examples of the black box. And the question is, what other tools we use in cardiology can be repurposed using AI? Something for us to discuss. Thank you.
Brilliant, thank you. That was an excellent talk, and both of you so far have stuck really well to time, so thank you for that too. I'm jotting down questions as we go along, so I've certainly got plenty, and I'm sure we'll get some from the audience by the end. But for now, what we'll do is we'll move straight on to the next talk. So this is Dr. Wasif Bukhari, who is the technical whiz on the panel today, because he's a software engineer at Citizens Bank, And he's going to talk about his doctoral research, which I believe is in machine-learned decision trees for cardiovascular risk profiles. So, Wasif, if I can get you on your camera, perfect. Have you got your presentation lined up and you're all good to go?
Yes, I'm all set. Thank you.
Brilliant. I will disappear and I'll come back on at the end of your speaking.
All right, thank you. Let me go ahead and share. All right, are you able to see my screen?
Yep, that's coming up.
Okay, so thanks for the introductions. Yes, so my name is Wasif Bukhari, and I am a PhD candidate from Arizona State, and I'm also a senior software engineer at Citizens Bank, and I've been working at Intel previously. So I'm not a cardiologist, as a disclaimer. So my research is I'm trying to predict cardiac disease using machine learning, to put it very simply. To go into more specific, I'm using a decision tree classifier, as I will show you later along in the slides. So the motivation behind my research, or the motivation, is that cardiac disease, it is the biggest cause of mortality worldwide. It is the single disease that takes the most lives. So it is a big impact thing. And it is also, cardiac disease is something that if you're able to identify earlier, or an early intervention can save lives as well. If you're able to identify patients who are at a high risk, it can be really life-changing. And that is what my goal is, to improve the prediction of the 10-year risk of cardiac disease and improve it more than what is currently being done using the Framingham risk score that most the cardiologists are using currently. So the techniques that I'm using to do that are addressing these two main challenges, and these techniques can be applicable to not only cardiac disease, but most predictive analysis in medical domain. So if you're trying to predict some disease, these techniques can be pretty useful. So the two big main challenges in medical domain that we see are, the number one is that the cost of false negatives is much higher than the cost of false positives. So what that means is that, let's say if somebody does have cardiac disease, so, and if you tell them that you do not have cardiac disease, it could cause a loss of a life as well, potentially, because they won't get treatment. So that false negative is very high, the cost. Whereas the false positive is also not the ideal situation, because you are still, if someone does not have a disease, you're telling them they have a disease. It's not as big of a concern than a false negative, but the goal is to reduce the number of false positives as well. So that's the number one problem in the medical domain. And the second one is the imbalance in the data set. So in medical data sets, what you often see is, as you can see in the COVID-19 case as well, that a lot of people get tested, but you do not have a lot of positive cases. So in our AI data sets, we have a lot of negative classes and very few positive ones. So that's also one of the challenge. So in the next slide, I will show you how I am addressing these two challenges. So for the imbalanced data set, what the most common solution is doing sampling. So what sampling is that you undersample the majority class and oversample the minority class. So the positive class, you will oversample. But sampling is not the best of the solutions, because undersampling, when you're undersampling something, you can remove some important data. And similarly, when you're oversampling, in our machine learning algorithms, it can cause overfitting, and it can also increase the learning time of an algorithm as you're increasing the data over as well. So the solution I'm proposing to handle the imbalanced data set is I'm using a decision tree classifier, but as the tree splitting criteria, rather than using the Gini and entropy, which are the most common splitting criteria, I'm proposing the use of Hellinger distance as that. So Hellinger distance is the difference between the two probability distributions and it is proven to perform really well on imbalanced data sets. So I have performed studies on that as well, and Hellinger distance is outperforming, is addressing the imbalance in the data set without the need of extensive sampling. So the decision tree classifier that I've modified it to use Hellinger distance as a splitting criteria. As well as a second, now we come to the second problem that I highlighted, which was the ability to control the number of false negatives. So I'm also calling it as asymmetric error control. So to do asymmetric error control, I am using an approach which is based on the Neyman-Pearson lemma, which is a mathematical lemma that we'll go into more detail. So traditional classifiers in machine learning and AI, only the scoring function needs to be constructed from the training data. So the threshold is chosen as 0.5 by default, as you can see from this graph here. The training data is only going towards the scoring function. Whereas the classifier that I've created, which is the asymmetric error control CVD classifier, is what I'm calling it. The training data is going both towards the scoring function as well as the threshold. It is being used to calculate the threshold as well. We're not assuming it to be 0.5. So the steps needed to add asymmetric error control for my classifier are the 3 steps listed here. So the first is sample splitting. So the way I'm splitting the training data is different than you do it typically. So you can see from the graph here, the training data is being split into 3. So it is in the mixed classes with 0 and 1 samples, the left out 0 samples, and the last is the left out class 1 samples. So this is for a binary classification problem where we only have we have positive or negative. So we have 0 and 1. So on the mixed classes of 0 and 1, we are applying our CVD classifier to come up with a scoring function. And then this scoring function is being used on the remaining class 0 samples to come up with a list of classification scores. And then the remaining class 1 samples are being evaluated to calculate the lower and upper bounds. So after we have the sample splitting done, then we are using order statistics to search for a threshold such that the classifier will always have the number of false negatives below a specific value that we will be specifying. So we can specify the number of false negatives. Let's say if I want to say that I don't want the false negatives to exceed 5%. So I can set my algorithm such that it will make sure that false negatives are under 5%. The accuracy might be affected a little bit, but the false negatives will always remain that. And that may be acceptable when you are predicting cardiac disease, where false negatives are very critical. So this graph here shows how my classifier accuracy varies with the upper bound on the false negatives. So if you see at the x-axis below, you can see that this is the number of false negatives. So 0.2 is 20%, 0.4 is 40%. So you can see that as and you can see the accuracy over here. Accuracy is the blue graph over here. You can see that as I loosen the upper bound on the number of false negatives, the accuracy keeps increasing. And then but using this graph, we have to find the optimal value of alpha so that the number of false negatives are reduced as well as the accuracy is also high. So as you can see, the upper bound is loosened up. The false negatives with this purple line is going up like this. So at this, I think this value of 0.22 value of alpha of the threshold, you can see that the false negatives are also pretty low. The false negatives are pretty low and the accuracy is pretty high as well. So this value will be the optimal value that we should be using in our classifier, such that we are reducing the false negatives to under 20%. And we also have an accuracy which is over 80%. So finally,
just going to have to hurry you up a little bit here.
Okay. So
we're about to run out of time.
Okay, so finally, how does the AC classifier compares with the other CVD risk prediction scores? You can see at number 4 over here, it has a ROC score of 0.82, which exceeds all the other Framingham risk scores and other scores that are being currently used. And this has been obtained from the data set from the Framingham Heart Study. And the classifier here is not only producing a better score than what is being used, we also have the ability to control the false negatives as well. So the summary is that we are able to predict cardiac disease using a tree-based classifier with asymmetric error control. And we have an ability to handle the imbalance in the data sets, as well as able to predict the CVD accurately with control over the number of false negatives. So thank you.
Brilliant, thanks very much. That was great, Wasif. And can I bring Francisco and Ashu back on? Can I get you to put your cameras on here, and we'll have a sort of a discussion and take some questions. We've got just under 10 minutes. We've got a bit of time here. So there were a couple of points I wanted to pick up on, but what we'll do is we'll go to the audience questions first, because they're more important than me. And we've got a question about the use of electronic stethoscope. So is anyone using electronic stethoscope data for detection and prediction of cardiac diseases, similar to the way people are using ECGs or EKGs? And if not, why not? So I guess, Francisco, I'll put that to you first.
Sure. The answer is yes. This company that produces these electronic stethoscopes that got the license from us to use the algorithm actually is using that for that specific purpose. And I think their plan is to expand this to the diagnosis of many other medical conditions. For this, it's important to clarify that we cannot just assume that the information we get in a regular 12-lead normal machine electrocardiogram can be replicated using the signal that comes from a stethoscope that is obtained in a completely different way. Just put in a little probe right here. So we actually have to do a validation test, and we actually prove that the accuracy when using a single lead representing what the stethoscope does was actually fairly good and similar to the accuracy of the full electrocardiogram.
But instinct would tell you that it's just, right, a stethoscope on a chest is a less sensitive, less data-rich modality, right? So you would just feel instinctively that there's not going to be the same kind of causal evidence mapping to the final disease. I'm using very technical terms, which I didn't mean to do, but you know what I mean.
Sure. There is some loss on accuracy, but considering how quickly this can be done and the simplicity of the single lead assessment, again, when we do an electrocardiogram, a regular one, it requires the patient to have wires in both arms, both legs, and a set of 6 different wires in the chest, compared to just a single thing that is put on the chest to detect that. Now, remarkably, this signal offers, I will say, an accuracy that we consider that is more than acceptable for that. I think the area under the curve for our validation study was around 0.85 compared to 0.93. So not that bad, though.
Yeah, that's really exciting. And I think that leads us on nicely to, I could just see another audience questions popped up that's actually relevant to what I'm about to say, is that I'm really excited about cardiac MRI. I've been amazed, particularly from your group, Francisco, about what ECG data, what the evidence that you can find using machine learning algorithms looking at an ECG signal, so much that the human eye seems to miss. And I think if that's true of ECGs, what are we going to find with cardiac MRIs? What are we missing? I mean, that incredibly rich data when you do voxel tracking and, regional stress, regional stress. I'm looking for the word to put on the end of that sentence, but you know what I mean? Gauging, measuring, and all, you've got the structure, you've got the function, you've got such a rich data set. But the big problem, right, is that you can do the study with 1 million ECGs that have been labeled. Whereas the UK Biobank's a fantastic resource, but off the top of my head, I'm thinking, somewhere in the region of 8,000 to 10,000 cardiac MRIs. Are there that many, Ashu?
Well, so most of the regular CNNs are actually trained on the UK Biobank, which is 5,000.
5,000.
Right, the problem that we have in pediatric cardiology is that there's never 5,000 of anything, right? We're never going to have 5,000 tetralogies, or 5,000 single ventricle of any of that. And so that's why we were trying to co-opt some of the adult stuff to see, right, if something's already working well on adult, can we just port it over to kids, just like we do with pharmaceuticals and we do with basically medical devices and everything else in pediatrics. And so, our training data set was 57 and our testing was 30. And, we're a pretty big center here in Dallas doing cardiac MRIs for kids. So, this solution to the problem of small numbers is going to be how we're going to be able to push this field forward in pediatrics.
Right. And you mentioned a couple of things I just wanted to pick up on, because we often get really mixed audiences at this event. So you mentioned transfer learning. What you were describing was doing fine tuning with a neural network, right? You trained it on normal adult cardiac MRIs. You then retrained it with the inclusion of your pediatric patients. Right. So it is possible to do that.
That was transfer learning. We just literally took the same network that they had trained the UK Biobank on, and then we added 57 cases to their 5,000 and then upsampled it. So we didn't actually change the algorithm at all or change the weights. But federated learning and transfer learning, and those are probably other techniques that we could have used or could have thought about in the future how we're going to solve that problem.
Yeah, brilliant. And just federated learning, for anyone who's not aware, is where you take a neural network and you actually move the network between different centers and train it in each center so that you don't have to shift any patient data. Shameless plug here, because I work for NVIDIA, who are big into federated learning. So I think I do, it's not really a shameless plug, because I think that's really exciting, because a major barrier to AI in medicine, as we know, is patient data concerns. So actually federated learning is a really interesting concept, isn't it? And for boosting numbers in rare conditions, where each center might have, 100 cardiac MRIs, as was your case, but times that by 100 centers globally, and add in transfer learning. And then final thing, because we've probably only got about 2 minutes here. I think those talks really nicely played into each other, because Ashu, you talked about automation of a process that's currently done by humans, which is enormously important, particularly in the post-COVID world. Francisco, you talked about superhuman stuff from a certain point of view, right? Because you're getting machine learning algorithms to do stuff that patients can't do. And Wasif, you talked about decision trees for predictive models, which is somewhere between the two. This is the question I had. I'd given you a heads up that I might ask you a question along these lines, and I promised that I probably wouldn't get this far, but I'm going to go for it, right? We talked about the dangers of what you were referring to, Ashu, where you train a cardiac MRI on a large number of patients, but then you apply it to a different population and it doesn't perform well. In technical terms, that's called covariate shift, right? And the human population is so huge and diverse. When can we ever trust a neural network if we cannot explain the sort of the rational scientific causal link that tells us how it does what it does? So at what point, Francisco, can we use your algorithm in clinical practice if we don't yet understand how it's detecting future incipient paroxysmal atrial fibrillation when the ECG currently shows sinus rhythm? It's outperforming humans. Therefore, how can we trust it? What evidence base do you need to see to trust an algorithm that you can't explain? Open question to anyone.
Sure, no, an excellent question, actually. I would be less concerned about trying to understand exactly how that works, because we do many things in life, many things we do with the mental processing that we don't even know how the mental processing goes, but we do it because it gives results. I will be more concerned about validating things like this in different populations, being sure that this is not specific for a particular brand of an ECG, that is not specific for a race or ethnicity, that it can be reproducible in different settings. I will say that as long as we can reproduce in a different setting, that will give more, it will be more robust.
Great answer, and I can see Anthony's just come on, which probably tells us that it's the end of the session here. So lovely note to wrap up on. Thank you all three of you very much, though. Those were three excellent talks and got us just skimming the surface of some really interesting subjects in this field.
Thank you.
Well, thank you so much. That was
an amazing session. I'm keeping my fingers crossed for my slides. Can you see it okay? I will keep going. But thank you for that session. It was just really great machine deep learning projects at work. And I think compared to a few years ago, it's amazing how this area has really matured in cardiology. So I'm going to invite my journal club faculty back on. If you could put your cameras and your microphones back on. I think I'm just going to use this. Can you see the slides, by the way?
Yeah.
Okay. So it's not who I voted for that made the slides go away. Okay. So so I just been tracking all the subspecialties, as you know, for the purpose of the book. I actually looked up every single subspecialty and what they're doing. So this is what things look like for radiology versus cardiology, and but the gap is closing. So since about 25 years ago, if you look up machine and deep learning and artificial intelligence, there's been just over 1,000 manuscripts from cardiology, but most of these papers have come in the last 3 or 4 years. So before that, it's been relatively quiet. But radiology's been, publishing this area since 2010 or so. So, and a majority is on image interpretation with deep learning. So if we look at the last, as I said, the last few years, it's really been a tremendous increase. And I think this year, despite COVID, we're going to go significantly higher in terms of number of publications. But I think we still need to do a lot more. I just picked three sample articles, not necessarily for anything other than the fact that they're good illustrations about how we use artificial intelligence. And as the last session has talked about, it's just, I think we could just be very creative using machine and deep learning. So this is, again, looking at COVID-19. It's more sort of a review on how machine learning has been used for COVID-19 in terms of cardiovascular complications. And by the way, I have summarized all of these articles in the takeaway document that I'm going to forward to everybody. So, and my thoughts about these papers. So I know our faculty may have looked at these papers, but the bottom line at the conclusion is that we're just not using it enough. So these are the ongoing sort of papers, but you can see most are case series, retrospective or prospective cohorts, meta-analysis, but very, very few are actually using real-time artificial intelligence. So we really need to focus on using it more. And I've listed in the summary paragraph of the takeaway document the few that are ongoing. There's basically 3. So it would be nice if it's 30 or 300. And I think the future is going to be real-time international databases for AI for cardiovascular complications. So any thoughts about that kind of concept? I know you guys alluded to this earlier. I know Luis is a big fan of real-time international databases.
I'm just watching if anyone else is opening their mouth. you fire away. You're going to speak, Ashu.
Yeah, well, I mean, I think, I think international databases are a great idea, but how they're implemented, how data safety is maintained, how, I think even in a local hospital, right, to say that the hospital can send the data to somewhere without consent from the patients, which, I think the data belong to the patient, not the hospital system that charged them for it. So, I think there are a bunch of limitations to be able to do that from a practical standpoint.
Yeah, in terms of data, patient confidentiality and the concerns about the data security, I think that's really interesting because that's such a huge barrier whenever you're in that field of clinical AI. I completely agree. But I wonder, has COVID changed the landscape here like it has the rest of the world? So I don't know what shape you guys are in the States, but here, things are bad. And the general public hasn't realized how bad yet because we're worried about COVID, we're worried about patients in ICU. And we're kind of vaguely aware of the fact that while all this is kicking off, we're building up huge waiting lists. I mean, waiting lists that would have been unimaginable at the beginning of this year. And we're gonna have to clean up that mess. You know, next year, touch wood, we get COVID under control. There are vaccines. Our health system cannot cope, and we have one of the world's best health systems. You know, people harm is going to come to people because of huge waiting lists, and we have to innovate. You know, necessity being the mother of invention. I'd love to see more effort in the patient-public involvement space. We call it PPI here, which always makes me think of omeprazole and stomach pills, but there's an acronym for everything, right? So I think the time is ripe after this winter, once things kind of settle down a bit COVID-wise, to go out and speak to the public again and say, listen, you know, can we strike a balance? How do you feel about your data, certain aspects of your data that maybe don't feel so sensitive and so personal, actually being released in ways they weren't before, in order to advance these algorithms that potentially could change the outlook of health systems across the world? And I think if we engage with people like that, we might discover that we can begin to loosen some restrictions.
Yeah, and I think, yeah, go ahead.
No, sorry, Anthony, you're far away.
Yeah, I was just going to say, you notice all of the action is on the COVID cardiovascular side. I've seen very little on what do you do with the rest of the patients who don't have COVID but still have cardiovascular disease. And I don't know what's happening in Europe, but in the US, I think somewhere between 25 to 50% increase in non-COVID related deaths. And some of that are cardiovascular patients who never got the care they needed at the right time during this pandemic. So, and yet I think those of us who are seeing patients, there's no smart way, even though there should be a way, to prioritize patients coming back. You know, we don't need, for a pediatric cardiologist, I don't need to do a follow-up on a child with a small muscular VSD during the pandemic, but I need to see the single ventricle Fontan patients, you know, as soon as they can come in. So, you know, there's so many uses outside of medical imaging cardiology, and in terms of workflow, logistics, and prioritization that I think should be implemented. But, you know, I think it's a wake-up call for how badly we need these tools actually. So hopefully we'll not just let the pandemic go by and not learn, you know, so.
I think the rise of social media and personal information being out there has changed, I think, sentiment, at least in the US, about whether your data are allowed to be used. But I don't think that's been capitalized upon to generate, you know, and then with fractured health systems and each hospital having its own system, you guys talked about interoperability a bit earlier, you know, at least in the US, how you know, even DICOM is just a header, right? It's not an actual workflow for how to make sure all the images contain the same information. And I think honestly, you know, there was a lot about data, you know, Dr. Sun, you were talking about data cleanliness and making sure the data are accurate. We, in our study, for instance, we purposely didn't go and recontour everything because we were trying to use clinical data as we used it to report the study. And, you know, if you have to go through every data piece 2-3 times, that's not fitting in the clinical workflow, at least for our cardiac MRI stuff. So, you know, I think they're like smarter people than me will have to figure out how to deal with those missing data and duplicated data and erroneous data and still overcome that.
Louise, I'm just going to jump in because we want to move on to the next paper. But Louise, I had the pleasure of visiting Louise's center in Canada. And I was impressed with the non-clinical aspects and the workflow that you've prioritized. So I'm betting that you had a prioritization scheme even before COVID. So it was probably convenient for you just to jump onto that scheme when COVID hit, right? Am I guessing right?
Right. So we do have a, implemented triage system for case urgency. And during the COVID period, we have been able to use that. But on top of it, what we realized was that the old scheme could be improved upon. And so that's why we developed some tools to help with the process. But I think, in terms of building an international database, I think 3 elements will have to align. So first of all, the individual database custodians will have to agree to join. And second of all, there's this big patient privacy and data sharing thing that has to line up, which will be a little difficult to do across state and provincial and national borders. And third of all is the interoperability issue that we're all talking about. And so even ICD-10 codes are different in different countries, for instance. So that's in a nutshell.
Let's move on to the next article. So I like these articles because they're for some of our audience. It's just starting to read AI and cardiology literature. These are fairly manageable. So this is the concept of an EchoNet. We've heard of ResNet and everything else, but it's a CNN for echo. So we're starting to see work in the echo realm. And 5 years ago, when I approached AI experts and said, how about deep learning for echocardiograms, and they said it's not quite ready for prime time, but we're starting to see now, at least with static images. And of course, I think if you tie CNN to a time series neural network, then you can actually do moving images, which is what I'm exploring, but it's not easy. So this is a paper just looking at structures and different things that look at volumes and heart failure and systemic phenotypes, which is interesting in age and sex, and look at how these can benefit from machine learning and different tasks. So this is just an example of what they've done. As you would expect, CNN for images of the echocardiogram study, not the entire clip, but medical images, and using a 75-layer CNN for outcome prediction. And I would say the results have been modest, certainly not great, but I think it's a great start, looking at static images, and of course, next will be moving images. So Dr. NVIDIA, Rob Risk. Yeah. So I've discussed this actually in NVIDIA at one point, and I think we may even talked about this when I was in London with you. So moving images, where are we? Where can we go? Is it ready? We're finally ready for that or no?
I think we're certainly getting there technologically. My suspicion is that in the case of echocardiography, the big barrier is going to be human variation, right? It's the human in the machine that's, because you line up 10 different cardiologists and ask them to call an EF, and you get 10 different numbers, which is I think remains for now a big problem in that world. If your ground truth isn't consistent, your network won't learn properly. So I have yet to see anything that really makes me think, yeah, that problem's been nailed. This framework works. Although it might be out there and I just haven't come across it yet. I think in terms of the image series data, I mean the size and complexity and sophistication of the neural networks we're now running. I mean, GPT-3 in the natural language processing world is mind-bogglingly huge. And we've seen what that kind of power can do, right? And the same thing's happening in the image world. You stack up layer upon layer upon layer upon layer.
If we learn from the previous experience, with just plain chest X-rays, it is going to perpetuate the differences in human interpretation. So it might even be more complicated because it's a moving image. So yeah, it's going to be interesting how we learn.
Yeah, but I have to say, you're ever going to find 10 clinicians who agree on the EF interpretation of an echo is, I don't think, ever going to happen. I don't think it's a problem that we can wait to be solved. I think we have to solve that problem from that. That's what I was saying about clinical heterogeneity. I mean, in pediatric cardiology, two people will argue about even what the kind of heart disease is on the same echo sitting next to each other. So, I don't think that it's practical to say we need to have the real EF, right, before we can train the networks. We're going to have to figure out some way to bake that uncertainty.
I respectfully disagree. I think we need to keep our sights on the ground truth as much as we can. There is a lot of too much subjectivity, I think, when I look at papers looking at this. There is going to be some sweet spot between, quote unquote, real ground truth, disease proven, hypertrophic myopathy, et cetera, to, the subjectivity that's, I think, a little bit too much right now, because I think we learn a lot about ourselves when we look at AI projects, because we realize
there is uncertainty within the diagnoses too, right? Like there's genotype positive, phenotype negative HCM. is that HCM or not, right? If they're not thick, but they have the, you know, I think there is some uncertainty in medicine. So,
Louise, what do you think? Let's go on to.
I'm actually stepping on a different tangent here, because when I think about those algorithms, what I'm really thinking about the target audience is actually those who are more novice to the field. Say, you know, this type of technology being applied to POCUS training, for instance, where, you know, you're introducing the technology to more remote areas or people who don't do this type of stuff very much. So they might need some assisted technology to help confirm their diagnosis. If in the middle of the night you're on call and it's a junior resident who's doing the POCUS, they could benefit from some measures of you know, interpretation in terms of what they're seeing.
Yeah, one of the things that we're thinking about in the pediatric space is because we don't have a lot of certain types of congenital heart disease that we need to really work hard on pulling our data. And I know it's a hard thing to do, but hopefully AI is the North Star that's going to get us there. So, okay, one more paper if we have time. And this is more of an adult paper. Just to give you an idea, it's just 3 papers to show everyone things are happening finally in cardiology. I think when I first met Rob, I mean, hardly anything was happening 3 or 4 years ago. And now slowly but surely, I think we're progressing, especially in the imaging area. And this is one that right up your alley, Rob, in terms of clinically significant or meaningful coronary lesions defined as greater than 75% stenosis. And in coronary angiography video, again, looking at CNN, looking at these lesions. And again, applying, and to their credit, to the Japanese center, looking at these stenoses. Again, the accuracy was, I would say, modest, wasn't good, but I think we're early stages, so appreciate the honesty and integrity of the as again, similar number of convolutional neural networks looking at these video clips. And I think what they're saying is this is particularly good for at some point maybe working in concert with the cardiologist in terms of looking at potential lesions that they may have not picked up. But given that it's 75% or greater, it's hard to imagine. But you know, this is where I think it's a good start, I think, in looking at coronary angiography. How about Rob, in your experience, have they started looking at coronary angiography?
Yeah, I think this was it was a good paper. I think it does highlight in some ways why we need more experience in the clinical domain of AI applications and where they're going to be applied. I don't mean that as a criticism of the paper, but what their ground truth here, again, it was I've only read this paper once, but from what I understood, their ground truth was a cardiologist looking at a coronary angio and calling the lesion. It was a very experienced cardiologist, but we know that doesn't work well when you look at OCT or IVUS with the coronary artery. So these are just for non-cardiologists in the audience, these are more sophisticated ways of getting a better sense of how occluded the lumen of the artery is. Actually, the naked eye calling it isn't that good. So their ground truth is kind of not a great ground truth to begin with. We know, I think there's a powerful paradigm here, because if you look at, FFR, which is fractional flow reserve, where you measure the pressure in an artery on either side of a lesion to work out how bad the blockage is, right? We've already got IFR, which is where you infer the fractional flow reserve. I think when deep learning will lead us into routes where we can be less invasive but glean the same information. So you get networks looking at the flow through an artery and the speed of the flow and inferring actually how blocked is the lumen. And then, plaque instability, because not every blockage in the coronary artery causes a heart attack. They're two very different pathophysiological mechanisms. So I'd love to see this technology. I'd love to see more clinicians have a really good understanding of the technology and its limitations and what it can do, and say, right, okay, here's the problem in cardiology where this thing really makes a difference. Because I think this was a great, this is a great early work, just showing that you can apply the technology in this world. But as we move on, we need to move a bit beyond this and think about the problems we're addressing a bit more.
Well, I think one of the helpful things, and you and I talked about this, is not necessarily, dividends like this, even though this is just more of a proof of concept. But tell me, Rob, from study to study, if I'm seeing a heart failure patient compared to 3 months ago, is the echo showing any significant difference during a deterioration phase or an improvement phase? That's helpful for a clinical cardiologist because our eyes, even if we put the studies side by side, may not pick up a subtle change that we need to, So, and then we add to that the RV stuff in congenital heart disease. It's really, it's almost impossible for us to show any improvement. So I think you're right that we need to somehow narrow the gap between the technologists and the clinicians to actually go after the things that actually will help us day to day. I think having an automated echo interpretation of a normal echo, I mean, how much time does that really save you, right? And even an accuracy of 0.99 on the AOC, I don't think it's that helpful. But study to study in a patient is very helpful. So, I summarized the papers for everyone's benefit. I think it's good just to start reading a paper or two and just get used to the vocabulary. Cardiologists are smart clinicians. They'll pick up on this very quickly and just understand the limitations. I think sometimes it's actually good to read the radiology references because they've gone through this already. They're a little bit more mature in this area and learn what the limitations are from their studies. I think it's very helpful for a cardiologist, and that we don't repeat some of the issues that have come up a few years ago with the radiologist. So, okay, with that, I think we're going to have Alexis or AJ come back on and show us how we can do the network sessions. And I want to thank Louise, Ashu, and Rob for helping me just kind of go over very quickly three papers in AI and cardiology. Alexis?
Right, so we're now getting into the time for the networking tables. So you should see an image on your screen here. It's just describing exactly where you need to go. So what you need to do is, if you're in full screen mode of the video, please exit out of it. Then scroll up to the top of your screen and you'll see the tabs. So on the tabs, please click the Social Lounge button, and that'll then show you the two images here. So you've got two tables, one that's looking into the overcoming the barriers to the deployment of AI, and the other, which is looking at the first pediatric non-invasive imaging collaborative. So you'll see the two moderators, their images. All you need to do is click on the button that says Join Roundtable for the table which you'd like to join. We are limiting each table to 25 attendees at each. So you, once the space is gone, but please do try the other table if you end up in a waiting room for that specific table. But thanks very much. Any issues, as I say, please just give me a little note into the chat and I can sort of work to try and help out. Thank you very much.
Welcome back, everybody. We have a special session for you that will do some real-time data science. So just to give you an idea that it's both easy and both difficult. So I think a lot of you have approached me about this possible session. So this is sort of a pilot for a cardiology meeting. So we've asked my friend and colleague, Kathy Jenkins, to present a scenario that a cardiologist might want to recruit you to help in terms of data science. And we have an all-star panel. So I'm sure we're going to solve this issue very quickly within 30 minutes, at least in terms of the outline, how you would approach this. So we have Rob, you've met, Rajmi, and Partho, and Chris. So it's a very stellar cast of people that do both clinical cardiology as well as have a data science background. So Kathy?
Yeah, well, thanks, Anthony, and thanks for letting me set up the challenge here. So I picked something that's really important in our field. In fact, the Congenital Heart Public Health Consortium has designated return to congenital heart care as a major, maybe the major, it's going to be their major focus public health priority for the United States, and I'm sure it's true elsewhere as well. The problem is that a lot of people who have congenital heart disease fall out of care. They either experience a significant gap in care or they fall out completely, starting when they're even 8 years old. And as people get older and older, they fall out of care more, despite the fact, and I showed some evidence here on this slide, that staying in care has enormous health benefits. There was a Canadian study that interestingly showed that CHD patients stay in primary care, but only half stay in cardiac care once they're 18 years of age or older. 40% of CHD patients entering adult centers have experienced a significant gap, usually in late adolescence or early young adulthood. Patients with gaps in care are at risk for more hospitalizations. And there's even suggestion that staying in care through adulthood provides a mortality benefit. This has been attributed to socioeconomic barriers and financial barriers, lack of access, and also people's perception that they're well, or even have been told at some point they don't need care anymore. So this is definitely a problem the Congenital Heart Public Health Consortium is trying to address. Our center has been trying to think about this from an AI and data science perspective. So I would really love to hear from the panel about how it is that you all think we should approach it.
All right. So I'm going to scribe, and maybe I can ask Rob to help me moderate as well, and to go through the typical steps that a data scientist would approach a problem like this. So, so I guess I'll start off. I think the number one issue that sometimes is actually one of the most difficult steps is precisely define the problem or the question so that it's a little bit easier to facilitate a data science project. Sometimes the problem is too all-encompassing and it's very, very difficult to sort of put data in the right place. So how would you, Kathy, how would you define the specific problem for us?
I think there's two problems, Anthony.
Okay.
One is finding people who are not in care, not in congenital heart disease care, and trying to re-engage them with congenital heart disease care. And the other problem is finding people who are at risk to fall out of care before they fall out of care and trying to do something so that doesn't happen.
Which of the two would you like us to take on?
Both.
Okay. Okay. All right. And so location of the patient and the
And I say that, Anthony, because as we've been thinking about it, the second one, it's a little easier, but most people think the first one is more important.
Okay.
That's why I said
okay. Let's start with the first one and we can maybe get that second one in there. Okay, so just finding these patients, and so their current state of care, would that be fair? And what the status is, right? Yes?
Yes, finding the patients and re-engaging them with care. There's sort of the action part too.
Okay.
Identifying the patients and re-engaging them in care.
Okay. All right. Anyone, any ideas?
So
It's a very practical issue. Yeah.
I guess the next step is another definition problem, which is define what defines the patient we're looking for.
So the American Heart Association, American College of Cardiology has segmented the population into mild congenital heart disease, moderate, and severe. And at least as we've been thinking about it, we've targeted the moderate to severe congenital heart disease group. So there's a group of actual conditions, they're listed in the guidelines that meet that definition. And so if you did have coded data with the diagnosis to a certain level of specificity, you could define moderate or severe congenital heart disease.
The way you phrase that tells me that we don't have coded data, right? That'd be too easy.
Well, you do in an EHR, for example. We do, yeah.
Yeah, I'll jump in here. So sometimes when I approach these problems, I think of it as the problem, the challenge, and the solution. So here I see the problem as patients with moderate to severe congenital heart disease fall out of care and therefore have worse outcomes compared to if they didn't fall out of care. The challenge is that we lose track of these patients because of our disconnected healthcare system, our haphazard insurance system, and we have no good way to find them to keep them in care. The solution is X, and that's where we start to think about it. So building on some of the things that have already been mentioned, what we've described, at least to some extent here, is the data problem. One problem with the current healthcare system, I would say, is that the fragmented healthcare delivery processes, the systems own the data. Imagine if the patients own the data. So that patient with congenital heart disease would own their own electronic medical record and take it with them wherever they went. So let's say there was some structured way, agreed upon structured way to identify patients who required ongoing follow-up. The patient essentially carries their medical record with them, like a bank card. So anytime they engage somewhere with healthcare delivery system, there could be some kind of alert. This patient has this moderate to severe congenital heart disease, get them in care. You know what I mean? But the patient has to be the source of the data, not the health system.
Okay. So given what we have now, though,
Rashmi, I will say that we had thought within one health system, maybe one institution or one system, exactly what you just said could be an approach. That if the patients were flagged somehow and then they hit the healthcare system, then that could be an opportunity.
It's like how Kaiser does mammograms, right? Everybody, you walk into the Kaiser system and anybody in that system, even the patient can order the mammogram because it flagged you didn't have a mammogram and you're in the guideline directed group for a mammogram, that type of system. But patients, in this adult congenital population are moving between healthcare systems more commonly than in other systems. So, in our case, we have Primary Children's here, and then we're the adult university hospital, and they end up with us or at a different adult hospital. So they got to take their record with them. Because it's also difficult for me then, because God, what surgery did they have? What was the original stuff? I don't know.
There are some countries that I've been to where every patient has a card with all of their relevant data, including their last EKG, et cetera. And they're Singapore for one. And then they're thinking about the next step, which is just uploading everything into the cloud that you'll have access to, obviously encrypted. So, so until then, right now we don't even have a president yet. So, so hospital versus patient would be ideal. I totally agree with you, Rashmi. But right now, Kathy, like in Boston, where would you find all of these patients unless would you just go through the Boston Children's Registry first?
Yeah, well, we were thinking of identifying the patients. In fact, we had done some retrospective data using the congenital heart disease, database, which has reasonably well-coded data, and doing some predictive modeling to see their attributes, for the probability of experiencing a gap or being out of care. We hadn't quite got to the part of exactly how we would find them if they came into the emergency department or primary care in our hospital. But, we could sort of envision you might be able to do that, similar to flagging patients last year, patients who need a mammogram or patients who need anticoagulation for their atrial fibrillation. It got harder when you went out of the institution, which is probably where many of the patients are.
I think it's appropriate that we're kind of stuck at the data, because this is where I think those of us who do data science projects probably spend less than 80% of our...
I have an idea. Yeah. Can I propose? So let's say the patients are lost to follow up. These are congenital heart disease. Let's say they are operated or unoperated. And let's presume that they are being seen by some provider somewhere, some primary care provider who does not know the implication of not having these patients seen by a cardiologist. Let's have an assumption. In that assumption, the opportunity is that if there are some of these patients are visiting some of the providers and they're getting some form of data collected. And let's say a rudimentary data could be an electrocardiogram. So you will have an opportunity here to take the electrocardiogram feature as a mechanism to identify existence of a treated or untreated congenital heart disease. And if that would be possible, the first step and the easiest step would be to kind of develop a software or app that would exist in the EMR, or at least you will distribute them to all the providers that will identify the features or the risk features that will flag a patient. Mm-hmm. So I'm just proposing one of the steps. So let's say, so it could be ECG, it could be an app connected to the primary healthcare stethoscope, a combination combined with some other clinical stored history that could be ingested in the EMR into an engine that will develop a prediction of the likelihood of this patient having an underlying treated or untreated congenital heart disease. I'm just starting.
It's a fun idea, the EKG, when we just saw this fantastic presentation on the power within EKGs, because EKGs for congenital heart patients do look very different, just done as an average statement. So that would be a really interesting opportunity.
Yeah, for data capture.
Mm-hmm.
Okay.
And a really novel identification.
Yeah. But the problem is there are plenty of congenital heart patients with a normal EKG too. So we'll be missing those. But yeah, certainly complete right bundle branch block would be a telltale sign that they had some RV surgery. So yeah.
But the hypothesis could be that they may be unknown or unidentified features. Let's say if you had a way to train up a model, some of this, some knowledge can come from the domain knowledge of us, like bundle branch block or changes in the ECG, but there could be other unknown features that could be picked up by the AI engine.
The vast majority of our patients in that population are just simply lost to follow-up, not because they have undiagnosed tetralogy or aortic stenosis. I think there are a few occasionally they'll slip through their teenage years without diagnosis, but those are relatively uncommon. How about once you have the data, what would be steps that you do to clean the data? Like how do you, because you'll have a lot of patients come through for the database and moderate to severe, how will we clean the data or wrangle the data?
One quick question I have is, so in terms of the ground truth for this data, what's the current process for obtaining that? In a sense of, how do we know whether they are or aren't in follow-up? At the moment, is it a case that you have records of patients that were known to have this condition, and then you have appointments of, kind of like a documentation of the appointments that they then subsequently had? Kathy, what does that process look like? And I guess if somebody
really
goes
hard,
elsewhere,
yeah, I mean, that's been really hard without, going through each record one at a time to even algorithmically define them. You can define who hasn't been seen within 3 years, which is how we did it for our study. But many of the times they were seen elsewhere. They just weren't seen in your system, in your database. Or they had developed, a change in their disease that became very minor. So the disease status had changed. That happens with certain subtle defects. So actually, the algorithms that we've used so far have failed miserably in detecting the ones that are truly out of care. We still think it's a serious problem. About 25% are out of care. We were wondering about using NLP algorithms. We had been talking to one of our NLP experts, Amir Kimi at Boston Children's, to screen the last text data and to try to understand if the patient really was or wasn't out of care before we would deploy anything.
I think if we're approaching this as a data science problem, then probably the generic steps we go through applied to this problem are define your data set, define your target class, because this is a classification problem, right? We've got an ECR, which is a big collection of data about lots of patients. We want to do binary classification on everyone. Are they a pediatric congenital heart disease patient who's lost a follow-up, or are they belonging to the other class that we're not interested in? So then we need to know what features we've got in our EMR, right, that we've got access to. So we've got unstructured data in the form of natural language and letters. We've got ECGs, which you've made reference to, and other modalities, lab tests. So we've got this big multimodal data set, and we've got a binary classification task at the end. So I think that's I think this conversation plays beautifully into the point Anthony always makes, in that data science, the actual algorithm, is the easy bit, right? Because once we've got to that point, then you just do the standard data science stuff. You codify the data. So NLP is all about these big language models that we talk about, but it's about generating numerical embeddings for language. And then you can start combining those models with your other numerical data. An ECG is a series of numbers. It's just, the voltage values for each sampling frame. And you can plug that into, could use a deep neural network, XGBoost, and anything. But I think the point that this conversation is illustrating beautifully is, in the real world, getting to the point where you've defined your data set and your target class so that you can throw it into a computer, right? You've already won. Yeah. Everything up until that point is the bit where like 99% of the hard work happens and the pain occurs. And it sounds like that's exactly what you're experiencing, Kathy.
Yeah, I mean, I suppose insurance databases might be an excellent choice with patients who happen to have that particular insurance. But yes, within the record of the children's, we only have what we have. It's exactly what you're saying, Rob. You're exactly right.
And
yes, go ahead.
I was going to say, Kathy, when you did look at it, did you find any variables that kind of had a degree of predictive power from the data set that you did have, or was it just a case that it didn't perform?
We're still cleaning the data in order to do that. The signals that we haven't found features that are directional yet. We were going to develop our plan was to develop a probability of falling out of care, and within the clinic, which is where we had control as a starting point, to implement risk mitigation to try to make it less likely that you would fall out of care. So using the probability value to guide action, and then going into the outer rung of someone coming in for an EKG or within our purview, or perhaps to the ED or the primary care network. But by that point, we just have a list of patients, who were out of care, and literally do it by the name. like as a name in MRN, not as anything more sophisticated. We think we're going to find a significant disparity problem where people have fallen out of care more if they're at financial risk or live in high risk areas, can't afford the co-pays and all of that. So we're struggling about how we'll solve that.
An important consideration also would be, Kathy, what do you think is the prevalence of these patients, or at least the as we try to go into the catchment data set, what do you think is the estimated? Because if the rarer the prevalence, more difficult it becomes. And I think there are certain degrees of challenges that come in developing classification.
Well, it would mean rare within the congenital heart population or rare within the total clinical population. They would be quite rare within the total clinical population coming into the emergency department or into primary care. We think it's about 20% of our patients that we should be longitudinally following have fallen out of care. So, and that's a large referral case. So that's going to be, tens of thousands of patients.
So I just want to say one thing. There is a kind of study, I think, that came out last year that it's a different problem, but I think there's some similarities. And it was essentially, it was based in London, and it was looking at what factors predict if somebody's at risk of not attending an MRI appointment. It was a Nature Digital Medicine paper. And with that paper, I guess there's some similarities in the problem in that it was kind of binary classification, like who's at risk and who's not. And they were trying to see what sort of features would enable you to then predict so that you could target an intervention to then encourage people to attend their appointments, or to at least kind of contact them, or like establish some way for them to re-interact. I guess here obviously is a very different patient population. It's a different kind of appointment. The second step of kind of re-engaging people with care will obviously therefore be kind of tailored based on that. But I think there's kind of definitely some parallels here, and maybe there's kind of some useful insights from that paper as well to think about. I think in that case, if I remember correctly, a lot of the factors that they found that did predict if people weren't going to attend were things like socio-demographic factors, whether people had missed appointments in the past, and those sorts of things, which, again, maybe that's something that could be incorporated here.
Yes. I will say, Chris, we did a similar study of pediatric patients who didn't come back recently for high risk imaging studies, and found the same thing. So there's a really interesting overlay with this problem and the disparities in healthcare problem in the United States. So I think that's a cross-cutting issue too.
Is there a possibility, Kathy, I'm just thinking off the top of my head, that you could do this exercise, but repeat the modeling process using only the features to be modifiable? Because if you develop a model and all it tells you is patients from socioeconomically deprived areas don't attend follow-up, perhaps that doesn't. Whereas if you strip that out and used, obviously we're talking about machine learning and AI today, but a machine learning model, if you forced it to only look at stuff you knew you could do something about, it might just be an interesting exercise if you had enough data. Yeah. It might tell you something you didn't know.
It's a good idea. You can do it both ways too. Yeah.
Kathy, going back to data location, a big basic problem that I struggle with sometimes, would the adult congenital heart program that you're in at the hospital have access to all the hospital data in the region?
Well, it always sounds easy, Anthony. We were just trying to use the Partners healthcare system. Well, yeah. It's now called Mass General Brigham, for those of you who don't know Boston. It's Partners is no more. It's now called Mass General Brigham. But they supposedly had, data from 10 large institutions all in one repository. Right. And trying to get access to it is actually really challenging. You have to go institution by institution. It's not like it's all one. But something very large like that, if you could tap into that with your list of vulnerable patients, that might work.
Yeah.
That might be big enough for some
Because
people.
you can just use an NLP tool and start looking for terminologies that would capture that patient. And I think, again, we spend 70–80% of our time just figuring out where to get the data, what type of form, where do you store it, how do you curate it, how do you fill in missing data, and those are the big challenges, I think. And then everything kind of gets a little bit easier. But it's very daunting when you're doing your first healthcare project. You just think, nobody ever really told me that the hard part is the data part. I always tell people, as Rob said, that is by far the hardest part. But if you can get over that obstacle at first, then the dividends is really gratifying. And we're finding that more and more. And you get used to struggling trying to get data, and you have a certain expectation and level of patience that you develop. But I think it's a challenge that can be overcome, that's for sure. So in the next 5 minutes, so I think what as a group, what will we recommend to Kathy? What are some
or to the Congenital Heart Public Health Consortium in the United States that could do something much larger?
Yeah.
Which is a network of all the major stakeholders in the congenital population, including the federal advisors.
Yeah. I'm also thinking, my 2 cents worth is, I was thinking something along the lines of what Ramesh is saying, which is make it a patient-centric and not a institution-centric. And that I find often very helpful, at least to think about. We're actually entertaining that where I am. I think the hard part is expecting the medical records to give you enough insight and when you're looking at a project like this. Something very straightforward, like I was looking at a project trying to find all the children that is in our system that has a genetic syndrome. Believe it or not, EHR doesn't just have like a nice bundle that you can go onto. You actually have to start listing all the ones you want. And I bet that's true for congenital heart disease. There's not a congenital heart disease bundle, and that would make things infinitely easier if you just have a bundle, a common code for all the patient cohort in that particular domain. And we've talked to different EHRs about having those bundles so that it's not a difficult, tedious process when you want to do a project like this. So
that's a really good idea, because that is something that consortium could create, is tools like that.
Yeah, just an EHR bundle so that you don't have to, with ICD-910 codes, so you don't have to start from scratch every single time that an institute is doing it. So any other parting words of wisdom there from our group for Kathy? It's a straightforward issue, but with some challenges. And I think all the more reason we need to really, as clinicians and as cardiologists, I think we need to learn about data. How do you precisely define the issue? It's like you have to bring your A game from your biostats days in medical school, to really clearly make a difference in terms of care. So I want to thank the faculty and also Kathy for always stepping forward and say, let's do something different with artificial intelligence. So thank you, everybody. And I think we will now transition to Francisco for, we were talking about natural language processing, and I think it's very timely because I see that NLP is going to have the steepest ascent in terms of capability in the next year or two, even more than deep learning. I think Rob might even agree with me, but on that
100%. Yeah.
There is hope, I think, with the transformer type of NLP tools to do what Kathy would like to do, which is just plow through records and find clues for patients to get re-engaged in the system. So Kathy, I think help is coming and just in time. So Francisco?
Yeah, Alexis, I think you need to give me permission to.
Okay.
Okay. It says you cannot start your video because the host has stopped it.
I think Alexis can do that.
Can you hear me? Okay, perfect. Right here. Good. So tell me when.
Yeah, you're good to go, Francisco.
Yeah.
Well, welcome everybody. We are ready to start the module number 3 that is going to be focused on NLP or natural language processing and workflow in cardiology. We'll have two speakers, and after that we'll have plenty of time for a good discussion and looking forward to have questions and to start the conversation. So without any further details, I will introduce our first speaker, who is Dr. Jai Nahar. Dr. Nahar is going to be talking about the role of clinical NLP, conversational AI, and virtual voice assistant in cardiology. He is an attending in the Division of Cardiology at the Children's National Hospital in Washington, D.C., and an associate professor of pediatrics at the George Washington School of Medicine. And I have been a pleasure to be with him in the ACC Healthcare Innovation section. He's the co-chair of the AI and Advanced Analytics work group. Yeah, your time.
So good afternoon, everybody. Let me share my screen. Sorry, just 1 second. Get the screen on. Good afternoon, everybody. Thank you to Anthony, Alexis, for the invitation and honor to present. And it's glad to be here on this session of NLP, and thanks to Francisco for the kind introduction. So I do not have any disclosures. For the talk today, I will go over basically it's a talk on the application of natural language processing and its subsection of conversational AI in healthcare delivery, including some introductory concepts. Sorry, just 1 second to get back my slides. So what is natural language processing? This is an AI methodology which allows the computers to understand spoken as well as written human language. Natural language processing is composed of 2 important sections. First is natural language understanding and natural language generation. So let's first look at the functions of natural language processing in the clinical care delivery. First and most important is the automation of data extraction. And in sessions so far, we have talked a lot about, and there is a lot of need for prompt data extraction, which is the first part to even generate the advanced analytics. So data extraction, especially the non-structured text data from various sources, including EHR. And the other important aspect is how to automate the data entry into the data registries as well. A good data automation will help in advanced analytics, which is including the real-time analytics and generation of intelligence and prompt insights, which will in turn facilitate prompt prediction, classification, risk stratification, which will drive efficient clinical decision support systems. The next 3 functions are applicable to conversational AI, which I will also touch later. So building upon these functions, let's look at the use cases of clinical NLP. I know Anthony and Dr. Rumsfeld in the morning had talked about how do we bring it out in real world. So this slide highlights the discrete categories of functions in which NLP can be used in clinical context. There are 2 important functional groups which I'm going to touch base today. First is on the right side of your slide is care delivery, and second on the left side of your slide is conversational AI. But other functional groups also need a quick mention. That is the MD workflow augmentation to decrease the physician burnout, Revenue optimization, which is very important. In the morning, I think Anthony mentioned about automatic pre-authorization, use of NLP in research. A forgotten component is the patient portal, and how can we augment the patient user experience for the patient portal. Let's look at the clinical NLP and basically its role in the care delivery. A big challenge in current healthcare data is actually a lot of data is trapped in an unstructured format, which we have heard from various speakers. How do we target that data? How do we get information out of that? As shown in this slide, there are two important steps. First is the data discovery, which is the major part actually, which makes the advanced analytics easier. NLP can be used to tap and basically can be used to get insights out of the input data from various sources. This would be unstructured data from EHR and other sources which we all use. This data by NLP would be converted into machine interpretable and structured data, which can then in the next step be analyzed using machine learning systems to generate phenotypic classification, risk stratification, which will drive clinical decision support, target early intervention. And in the morning, we did talk about performance measures and basically how we can use NLP for performance measures to find out gap analysis, improve and quality improvement and improving outcomes for the patients. This is a little old example from 2018, but this is a real world application of NLP for data mining from the EHR. Mercy, a St. Louis-based health system, actually collaborated with Medtronic for this NLP project to data mine the data for heart failure patients from the Epic EHR. There were two important functions for this project. Number one is how to improve, how to evaluate the performance of the CRT devices in the congestive heart failure patients and give that feedback back to the Medtronic so they can kind of improvise on these devices. Second and most internal function was actually how to help the clinicians take better care of the patient's congestive heart failure based on the data-driven insights and intelligence. So similar models can be used in other cardiovascular conditions as well, which leveraged NLP with the EHR. Now changing gears, next application of NLP is in conversational AI. The foundation of conversational AI is natural language processing. And this is a technology which allows human-machine interaction through the use of natural conversation using voice user interface and machine intelligence. In essence, it's a synergistic convergence of voice technology, natural language processing, machine learning, and deep learning. In the current conversational AI ecosystem as relevant to healthcare, there are three important components which you had mentioned. First is chatbots, second is virtual assistants, and the new upcoming technology of ambient clinical intelligence, which I'll mention as well. If you look at this slide, there are four value-adding components, four value-adding touch points of conversational AI in healthcare delivery. Starting from the top of your slide, first is at the point of care, at how to decrease the physician burnout and decrease the administrative tasks. Second, at home, how to help the patients for home health optimization. Third is in the call center, how to optimize the customer care. And fourth is in the hospital, how to ease the patient's hospital journey. And one important application of conversational AI is actually, which is forgotten and which has got kind of good role, is chatbots. Chatbots are basically conversational agents which can be used to fill the gaps in care access. I know we talked about the care access, so chatbots are one of the agents which we can use strategically to kind of fill up that gap. They can be used for digital triage or e-triage, which are patient-facing, especially for extending the access from the real, from in-person care. During the COVID-19, peak of COVID-19 pandemic, there was a high demand and the chatbots came very handy. As shown in this slide, there's a CDC chatbot, and also these kind of solutions can be used, can be customized for various cardiovascular conditions to optimize the virtual cardiovascular care delivery. Next, a very important application of conversational agents is voice-enabled virtual health assistants. This slide highlights the 3 important functional groups, basically in the functional spectrum of voice-enabled virtual assistants. At the bottom of the slide is the assistance to the patients for information, for care navigation, and for patient education. Middle is a digital interface. These virtual assistants can help to provide a seamless digital interface between the patients and providers to facilitate remote care monitoring, which is coming up as an important component of virtual care delivery. Third, a very important component is facilitation of care management and wellness. This is of high value for patients, chronic patients, and those who are high-risk patients, such as congestive heart failure, diabetes, and hypertension. We need to mention a word about a new emerging solution for conversational AI, which is ambient clinical intelligence. Microsoft and Nuance have partnered to bring about this very intuitive solution, which is ambient clinical intelligence. It is a comprehensive voice-enabled AI solution. As you can see on the slide, it has got 3 important components. First is an ambient sensing technology, which employs computer vision and conversational AI. The second is user-initiated virtual assistant, and the third is automated documentation. So basically, this conversational AI solution helps to decrease physician administrative burden, burnout, and increase patient experience. It does it by 2 important functions, especially at the point of care. The patient-provider interaction is documented without physician's input automatically into the patient's chart in the EHR, which physician can later edit, which would solve a lot of our administrative burden. Second is also help physicians to navigate information from the EHR and get the information in and out of EHR by use of voice-activated virtual assistant. A quick word I want to mention about from the talk this morning. There was one conversation about how do we bring out the solution, fill the gap for patients for all level of clinicians, like from medical students, residents, and for the advanced, senior cardiologists. Basically, a virtual care assistant, if it is voice-enabled virtual assistant, is integrated in the EHR, which can learn by the user queries and user profile and user needs. That will be a great asset for for the future. So looking ahead in future, thought should be given to first is use of integration of NLP in multimodal data fusion. And I know in the recent conversation, it was mentioned about basically how we can fuse, not only looking at the patient as like looking at 360 degree of the patient, how to put NLP imaging data and the data from various sources to have a full 360 degree view of the patient. In fact, gather a contextual AI. That's how the human clinicians think. We don't just think of language or just the data, but we look at the patient in whole. Second is actually thought should be given to development of smart EHR systems, which integrate natural language processing and conversational AI agents, as I just mentioned. Third is development of advanced human-computer interaction. So a possible solution can be proactive virtual assistants with cognition and empathy. In conclusion, the natural language processing is an important AI technology which can help in unlocking actionable insights from unstructured data, which we all grapple with. Conversational AI agents can be used as intelligent user interfaces, both patient and provider facing, for augmenting healthcare delivery. And last but not the least is user experience, smooth workflow integration, data privacy and security is integral to successful implementation of NLP and conversational AI in healthcare delivery. With that, I would like to thank you for your time, and we'll be happy to take any questions. Thank you.
Thank you. Thank you very much for your presentation. I'm pretty sure we'll have enough time to discuss those things. So I will just move to the next speaker. And our next speaker is Dr. Partho Sengupta. I actually have the opportunity to know him for quite some time when he was a fellow here at Mayo Clinic. He's going to be talking about AI for augmenting diagnostic workflow in cardiology. Dr. Sengupta is the Avinash Yain Chair and Professor of Cardiology at the West Virginia School of Medicine. He's the Division Chair in Cardiology and also the Director of Cardiac Imaging and the Chair of the Cardiovascular Innovation at the Heart and Vascular Institute. Thank you, Barto. So the time is yours.
Thank you very much, Francisco, and hello, Jay. I'm really thrilled to be here back. And today what I'm going to do is to give you a 10 minutes overview of what practically we have done at West Virginia University with regards to AI and application. And if people are interested to really taking it practically to solve real world clinical problems, perhaps I might provide some of my experiences that we have had. 4 years back, I moved to West Virginia from New York. And the challenge was that we are confronting a state and we were trying to develop a statewide program where there's a huge burden of cardiovascular diseases. And as we know, this is reflecting of what is happening globally and maybe across several regions across in the country as well. And the other challenge is that while the burden of disease is increasing, we do not have an equivalent increase in, at least that's the projection, that will not have an equivalent increase in number of medical professionals. So there's going to be a shortfall. And the solutions that we need to think about is how do we do automation? How do we maximize our efficiencies? And I think AI in combination with other digital technologies are going to play a very important role. And we started planning for doing that in West Virginia. The first step we did was we were successful in getting a grant from National Science Foundation. And we tried to create an enthusiasm and an appetite here. And this is very important. You need to have people engaged. And the whole idea was on one side in the clinical institute to introduce AI. How do you introduce AI? Nobody has learned it, at least some of my colleagues and others never coded or never had an idea about how to use AI. We use statistics. So the first important step was to find resources for data scientists. And that's the number one step. So I think I continue to do that and emphasize, even if I run my own programs, the first thing is to run yourself and then go and find your partner data scientist. And this combination of having a data scientist partner and engaging with them actually allowed us to think like the data scientist and to design our projects, which was the first thing that we try to do. And the whole idea we placed was how can we provide appropriate identification of higher risk patients early on and triage them. So what can we do in the outreach locations, far in the communities? People have to travel 3 hours away to tertiary care facilities. We need to do something out. So the immediate answer, we need to develop tools that are going to be able to detect patients and their diseases out in the communities. And then once we detect based upon the app or the tools, the digital tools, we develop a process of identifying and risk stratifying and predicting the risk early on, projecting it and bringing them in the inpatient environment, where you further do diagnostic testing to corroborate your initial suspicion, and also use technologies, machine learning technologies, to model the solution. So, and everywhere in this process, you're engaging with people, providers, EMRs, data sets. You're also engaging with tools, and we also introduce new digital tools, variables. At least simple variables like ECGs that are available and can be diagnosed on finger using fingers placements, a live cord, for example. So after we put and created the enthusiasm, next thing was to create new leaders, new people, the fellows and the research teams, so that these solutions could be taken into the labs and you can have a reverse translation and brought them back. And the other challenge that we were trying to build in was how do we redefine cardiac diseases? Because what we know of valvular heart disease doesn't seem always the case when you come to data science. Data science is far more complex and highly dimensional. There are social determinants of disease, there are clinical factors, the diagnostic data, there could be also lab tests and biochemical data. So it's a high dimensional problem, and that needs to interact with the wearable data. And we introduce pocket ultrasound images. How do you make sense of all this information? So you start developing the problem in terms of identifying disease, not in terms of our mechanistic understanding in how we define in pathology, but how do you define disease in the data science? So you have to almost derive a new taxonomy for defining what will be characterized as a disease, sets of constellation of features from all these different sources that will be connected to outcomes of interest, or at least then we can use our domain knowledge to define, oh, okay, so in the variables, valvular heart disease looks like these kind of features. So introduction to a new taxonomy of cardiac diseases was needed. Thirdly, we also utilized our previous experience from global programs. So connecting with the global opportunity using American Society of Echo and ACC, we reached out to data sets which may be resembling a rural data set. For example, data set from India or data set from some other country. And then using this variable-based data sets or any other data set that we develop the machine learning model and see if that can be applied to the rural frontiers of West Virginia. And this is important because if you want to develop a machine learning model and test for generalizability, it's very important that it should be translatable across geographies and over time. And here is an example of an active event. This was an ASC event where we collected data in 3 days at 4 different sites using all kinds of technology. In fact, there was tremendous enthusiasm. And in this technology, also we tested the question whether people and their interaction with digital gadgets, telemedicine is very common now in COVID-19, but not at that time. How do people find when they interact with their data extracting tools, potentially in the future, robotic tools, before they even see a doctor? So this paradigm was tested, and it's being analyzed. We have a follow-up data, and we have not seen, in fact, we do not see that there is any adversarial relationships between patients and physicians. So this was an important step, particularly for rural environment. Here is an example of a condition we commonly encounter. Anything in cardiology starts in diastole. When a patient talks of shortness of breath, it's basically because there's elevated filling pressure in the LV, and that goes back and congests the lungs. So the question was, how can we identify shortness of breath and connect it to diseases, be it valvular heart disease, heart failure? And here we looked into a simple extraction tool from simple surface ECG and trained a supervised machine learning algorithm and tested it out not only in test sets within the location in West Virginia, but we had a separate institution in Canada as an external validation. And you can see this red and the and blue lines are internal test set and the external test sets. And this is extremely critical, generalizability of the data. Now we have a tool using simple surface ECG, we can diagnose elevated filling pressure. And that would be a best triaging patient from the community to those who need to be seeing consultations or reducing the load on our diagnostic imaging laboratories like echocardiography, where 30 to 40% of the studies may be just normal. It is a burden to the labs to do these normal studies, and better triaging, more appropriate studies would be helpful. So this was the reason we did this particular study. And the same is going on across the world. We started using very early on automated tools for interpretation. If the patient is then brought into the lab, how could we fast accelerate the process to go through the entire interpretation and and a generation of the report process. So how can we automate that with standardized outcomes? So tools were tested here, and this is another study that was in circulation, which shows not only you can automate the interpretation of the echocardiogram, but you can diagnose diseases with the same degree of accuracy. Otherwise, that would come from a specialist. And this has happened across in all modalities in cardiology. So it looks like AI is taking over majority of the steps for measurements and interpretation. And this change is going to continue, and it will allow us to evolve even further. The next change that we are looking forward to is developing, and which is work in progress, is developing better risk stratification. AI is fantastic for predicting risks and works better than other statistical algorithms. And you can keep on adding lots of data. For example, if there's a CT-based coronary calcium score or coronary angiogram done in a young patient, and think about, you could enrich it with facial features, retinal images, sensors, echocardiogram, whatever is there available in the environment, and predict the patient's likelihood of getting hospitalized or an event happening. And this is happening, and this is coming very strong. And I think risk stratification scores are using more and more AI algorithm and allowing us to identify patients early on who deserve to be treated with more rapid course of actions. Another interesting aspect we learned very quickly was that we cannot always train supervised learning. I mean, there's a lot of data which is unstructured. For example, Jay was talking about unstructured EMR data. We don't understand that. So the unstructured data and a lot of unstructured elements of our diagnostic data, they are not connected. In fact, we don't even use them. We are on the tip of the iceberg. This needs to be harnessed and farmed. And the only way to connect all this unstructured, ununderstood data, we need unsupervised learning. And so there's supervised learning where you can develop tools, but you have to understand that you may need to understand the whole field of cardiology or a whole field of any discipline by parsing it out based upon the existing data and connecting that and developing completely new ontology of disease. And this is going to be the step that is going to be critical for re-understanding the whole medicine or whole syndrome cardiology. And this is one such step that we attempted using a semi-supervised model. Semi-supervised means combining an unsupervised model, understanding the disease, and then training the algorithm to based upon the knowledge that you've learned from unsupervised learning. In this, we can see here clustering where diseases or patients are clustered in different nodes. And you can see these red dots here are the people who are dying. So you suddenly recognize that this group of people are dying, and you start giving them a label, a new label. Oh, this is a high risk feature or a high risk disease group or XYZ phenotype. So this is coming completely from unstructured. And then once you do that, you test it out and see whether it predicts the outcomes in a supervised model, and it does. So this is the area of semi-supervised learning, which is going to play a major role in the future. And we are investing heavily into unsupervised learning of cardiology at the moment. So if I have to summarize, therefore, that machine learning is here. Enthusiasm in adopting it starts by building the bridges between data scientists and also physicians. We have all to partake in this whole process and learn it. Maybe many times machine learning does not work well, understand the biases in the data, type of the data. There are lots of new knowledge that require to be understood before designing. But once you have done it, it allows you to free up time from your mundane activities. And it looks like it can allow and give us more time for higher caliber work, which is very important because we are struggling to find time for our own thinking. And once you have the more time that is created for higher level of work, AI is not going to replace you, but AI is going to connect you more with your patients. and bring you to higher wisdom and personalize and foster patient engagements in a better ways. Thank you very much.
Thank you, Partho. That was a very nice overview on all the wonderful things you are doing there, and actually an example of how we can integrate all the different steps of AI, from NLP, automatization, standard supervised learning, and unsupervised learning. So we have a little bit less than 5 minutes to discuss. So let me start with one question. A question for Ye, and obviously part of it, feel free to contribute too. Any successful cases of conversational AI that you can share with the group that are right now being implemented or that have been implemented already?
So I can talk about a very good intuitive solution of conversational AI from Boston Children's Hospital, that is ERAS program. Kathy might be able to kind of shed more light on it, but basically it's for post-cardiac surgery patients. Actually, when these children go home, using Alexa as a voice user interface, and actually coordinating with the parents about how the child is doing, getting the report on day-to-day basis. Actually, that is just more like a remote follow-up, patient follow-up after the procedure. So similar models, and this has been there for past few years, at least I know. The other similar solutions can be used, can be extrapolated to the other post procedures as well, as like post-EP, post-cath. Those, and it can be also extrapolated to the adult world. So not only procedural, but basically, other high-risk patients such as like transplant and cardiomyopathy, heart failure patients. So that is at least one good, voice user interface and basically virtual assistant solution I came across.
Good. Have you seen any case where they use, voice-specific NLP or conversational AI intermixed with voice analysis for, there are some reports on screening for depression or even heart failure from Israel, because the potential is huge. When we combine the voice recognition, conversational AI, and voice analytics, trying to not only establish a communication, but also trying to detect a condition or a mental health status. Any thoughts on that?
You bring out an excellent point. Actually, just in interest of time, I did not touch it, but that's basically voice biomarkers, extending the spectrum of conversational AI. So basically, whenever there is any interaction between patients and providers, we get the data. So we get everything like data and metadata, but voice biomarkers are important. Actually, upcoming, at least I know in pediatric world, there have been some studies about risk stratification for coronary artery disease. Basically, they use various like sections of the voice, the phonogram itself, basically, which is used kind of further as voice biomarkers. An important application which we can think about is actually heart sounds, the phonocardiogram as a biomarker, which you are telling about echo, and actually Partho has done more on the EKG aspect of it. But at the remote level, when we are following these patients, actually, you're asking them to put a remote stethoscope, maybe an echo version of it, and then developing insights just from the heart sound as well. Because if you look at the phonocardiographic tracing, there is much more beyond like what you have done your work on from the EKG perspective. Partho has done his work on the, from the diastolic signals as well. So it's basically like signal processing. That's why, I would come across voice biomarkers in conjunction with the plain, simple conversational AI.
Partho, any thoughts?
Yes, I think voice is a tremendous source of information. I've seen some work on using voice as a marker for frailty, for example, when you encounter patients and you're deciding about the frailty of the patients and how frail they are. The quality of the intonation of the voice can provide you ideas about frailty. Now, one project, and it's not directly a voice, but I think it could be extended, and we have attempted to do that as a pilot, and we're trying to do that as a pilot, is in patient engagement, and from the intonation of the voices of the patient, you can do sentiment analysis. From the text that they type, you can do sentiment analysis, and you can actually predict no-show, or if patients are going to be compliant, or is there's a risk that they are not going to take their medicines when they go back home. So there's all this tools are exciting in terms of the levels of opportunity that they present. Yeah.
Good. Well, thank you both of you, Jay and Partho. That was a great session. We have to finish. There will be a call for break right now. Thank you for your time. Exciting things. Really, just we can continue on and on. Thank you for your presentations.
Thank you, Francisco. Thank you, Partho. And thank you, everybody.
Yeah, wonderful.
Welcome back, everybody. I apologize for an unstable internet. My children are all learning from school, so that's the price we pay these days. So welcome back. What an amazing 5 hours. And first of all, I want to thank John Rumsfeld, the American College of Cardiology, for being such an amazing partner in this meeting, and GE for their contribution. So thanks, Gil. And also the faculty has just been stellar. I was just telling our faculty that in a space of 3 or 4 years since we had our first meeting on AI and cardiology, both the breadth of the topics as well as the depth of the discussions is just, geometrically increased since our first meeting. So, so exciting. Now, as the things aren't complicated enough, we're gonna try to bring in some discussion about ethics as well as bias and implementation. So all the real world issues, and in addition to the data science. So I want to introduce our faculty, and we have Mike Fisher from Liverpool, and Francisco's back. We have Jaritha from just up the highway from me in Palo Alto, Agil from GE, and Kathy, a really old friend and colleague of mine from Boston Children's Days, and whoever else wants to be part of this. So let's go right into it. What's your, for those of you who have been through some of the sessions, what's been the number one takeaway for you? Who wants to go first? Just raise your hand, and then we'll use that as a sort of a forum for discussion. Jaritha, okay.
Yeah, I'll take the easy bait here. But I think the biggest takeaway is that it seems that people are really passionate about this. And that's, I think, the most exciting part. It often feels like each person is working a little bit in a silo of trying to get this to really get off the ground. I'm in pediatric cardiology, so I think that seems even more removed than maybe what's happening in the adult world. But I think mostly this meeting was amazing to just see how so many people are committed to really getting AI and cardiology and how it can impact our patients really moving to the forefront, and recognizing there are a lot of challenges that come with that, but that people are excited and willing to move forward with it.
Yeah, well, as I said, cardiology, and particularly pediatric cardiology, because of the small numbers of patients and categories and the complexity, cardiology is just so ripe for adoption of these technologies, and the timing couldn't be more perfect. Anybody else?
Yeah.
Kathy.
Yeah, I was just really excited to see that really the depth and evolution of what was being discussed. And I really like a lot when people are pushing the AI-enabled tools, broadly speaking, to show us things that we don't already know. And really the talk earlier about the power of EKGs, which I think was just amazing, with showing the point that I'm trying to make with a real simple tool, but there's a lot more there that we haven't really had access to, and these tools are giving us access. So I was just really excited about that.
And that ties in nicely with our last talk about the power of unsupervised learning, which is just, I think, rich with clinical insights, and textbooks will have to be rewritten because it's not that they won't be relevant, it's just that there'll be so much more information from looking at the data from the bottom up rather than listening to all of our mentors from the top down. So Mike, did you have what did you take away from today?
Well, I have to apologize. I've been, because I'm in a 5-hour removed or 7-hour removed time zone from you, I've not been able to join you much today. Okay. But I'd just like to comment perhaps on one of the things that I think Christina said, that I think particularly with this section being on kind of ethics and bias and so forth, one of the things that I've noticed is that the enthusiasm for all of this is actually a kind of a double-edged sword. And one of the things that I've noticed is that I'm having to work really hard to try and balance the people's enthusiasm. I'm not wanting to kill that with regulation and with governance, which of course, you know, is so easy to do. And I've said before, the NHS is an absolute master at doing that sort of thing. I suspect more, I think it's better at that than any other healthcare system in the world. If there's one thing that the NHS is better at than any other healthcare system, it's killing innovation.
It's a test of your will.
Yeah, well, exactly. But, you know, on the other hand, of course, the fact is that this is a very new technology being deployed to guide real things to real people who are unwell and vulnerable. And it can't be treated in exactly the same way as, you know, innovation in the gaming industry, for instance. And so I think that's one of the very interesting things about this, that on the one hand, you have this great enthusiasm of push, which comes from, you know, the whole sort of innovation kind of space. And yet, on the other hand, it's important not to kind of forget some of the issues that can arise because of the relative newness and some of the unknowns of the technology. And we have seen some of that already, of course, with, you know, things like learning sets being taken from very unsupervised pools of images, for instance, and the metadata coming down with those being absolutely not what you would want. And, you know, I think people will probably know about the incident where a database AI system that's being used to recognize faces scraped a load of images and metadata off Google, essentially, and ended up with metadata that contained a whole variety of abusive and racist labels, which the computer then, of course, perfectly innocently applied to some of its training set.
Well, I think, yeah, I want to come back to that when we get our takeaways from our other 2 or 3 faculties, because I think that's a great construct to begin our conversation. Gil?
Yes, I think one thing that struck with me, and it was Dr. Rumsfeld who talked about it, how important it is to think about how AI should be implemented in practice, all the way from the point of inception of that idea or that project. And you know, there's a lot of barriers that we might have, both in developing AI. We discussed in our roundtable about you know, technical barriers or funding, or it could be you know, barriers related to who's paying and value and so on. And I'm thinking a lot about, you know, how to take already existing AI models, and there's been a lot of good examples here today from Sengupta and everybody else, how to more quickly get that into clinical practice, and the scalability of everything. You know, we've been dealing with developing AI in G for several years now, and I think in the beginning we thought we could do this really quickly, and then we start to learn about all the challenges, and as some of them are starting to be cleared away, I think we need to think about scalability and how we can accelerate. One thought that also came up today, I shared with the panel here that I participated in a European discussion about health technology assessment this morning. So engineers and developers are often you know, motivated by developing a new AI algorithm, getting it through regulatory clearance, get it out there as a product. And then health technology assessment, which is a lot about, you know, risk and management of value creation for providers and patients, that sort of kicks in after, when it's out there, the post-market. And there's really a need to collect post-market data to be able to monitor the potential harm and also the value that we are creating. I think this is actually where regulators and developers will start to have aligned incentives, because getting real-time data from models as they perform in the field is going to be very important for regulators. But it's also going to be very important for innovators, because that's all what AI is about. It's about getting data, improving the models based on that sort of closed loop. So that got me excited, actually, that in some areas, post-market surveillance, regulators and innovators will go hand in hand. We both want to get that data back and make the models better.
Yeah, that's our collective vision, right? Is everything real time? And I think this pandemic has really been very painful not to have that, right? In terms of, I mean, just look at the ICU people that are working on the front lines and texting each other about what's working, and took 2 or 3 months to realize that proning actually was pretty efficacious. So just no excuse for that. Francisco?
Yeah, a couple of observations. One is, it is very nice to see how AI in cardiology and in healthcare in general has been evolving, going from being primarily a field run by engineers with amazing ideas and amazing algorithms with probably very limited real life applicability. I remember those situations like, you can identify when the person smiles, and then you're like, okay, so how can I apply this to my, right? So right now we are seeing actually a convergence into real application. Now that brings us into a new territory with a number of challenges. Number one, the dissemination of the results is more and more challenging. Journals don't have reviewers with expertise, and as soon as they find a little thing in there that they don't like, they just reject it, no matter how amazing your protocol, your algorithm might be. And that's a disservice to science, because they're publishing a lot of, I will say, garbage coming from, retrospective data from 1975, whatever. But these things are being rejected because the area under the curve was not above 0.95, right? When there is no biomarker with an area under the curve that has an AOC that high. So the other thing is that as we are moving very fast.
I just want to bring up the point is, some of us say the perfect model could have zero impact. So,
yes.
Yeah.
Now, however, a real challenge for us is going fast enough to continue with this momentum, but at the same time be very cautious, not to go too fast that we lose credibility. Because some of the early algorithms that we're lucky enough to get FDA clearance, I don't think they will pass that clearance right now with 100 patients with no validation, no confirmation that they are free of bias, right? So we have to be careful how we move, because we have a number of situations where the algorithm performed very well here and was totally useless in a not necessarily two different population. So I think we have to go from this life cycle of AI, to go from the idea to the testing, validation, and validation in different settings, different ethnic groups, different countries. I think meetings like these help us to recognize faces, network, and facilitating that. I think that's going to be a critical step.
Yeah, I'm a total believer that you shouldn't innovate exponentially without stopping. I think it's good to have a few pauses and cognitive pauses just to think about it all, right? Because technology is just going to surge, as we've seen. So, Kathy, did you raise your hand?
Yeah, I just wanted to add on the implementation side, we're just about to implement some algorithms in a very, I don't want to say metastable, but a very high risk area, our cath lab. And guess what? The algorithms aren't perfect. And so we're actually, we're going very carefully, but we're borrowing a tool that we had developed called SCAMPS, the Standardized Clinical Assessment and Management Plans, that some of you in the field might have heard of. It was really a framework for improving healthcare rapidly. And one of the critical issues with SCAMPS is that if you don't like the algorithm, you simply divert from it, but you have to say why. Okay, and then we're going to collect some data about what happened. But it really did solve some of the unexplainable AI problem, or the algorithms aren't perfect, or just the hesitation to get going. But what we're realizing is, by that simple part about you have to say why, it's also going to be critical intelligence for us to understand maybe how to go after making the algorithms more clinically intuitive. Yeah. And so we're really excited about that, because this gap to implementation is very real, and we need some tools to get past it. And this is one that a lot of work went in. It was just not quite ready for prime time when we developed it, but we're repurposing it now.
Yeah, I think one of the best dividends from AI in healthcare and clinical medicine is, as I found out when I was going through school, is you learn a lot about yourselves and about how you handle patients and how you are as people. Because it's kind of a reflection of your thinking process in many ways. So it's like raising a child. It's, you know, there are a lot of you in that algorithm. So it's just so important, because sometimes we displace the accountability and responsibility, like, oh, that's AI. But AI in a way is a misnomer, because it's really human derived intelligence into machines. So we shouldn't, you know, we're a little bit unfair sometimes to AI in the sense that we kind of displace our accountability. Needs to be a little bit more symmetrical. So let's come back to Mike's construct here in terms of AI and bias and ethics. And one of the best questions I think I've had in the last year or two was in Australia last year. And someone said, you know, Dr. Chang, can you comment on the ethics of not having AI? So sort of the counter argument about ethics of AI, because we're very nearly obsessed with the bias being perfect, the algorithm not having any ethical issues. But what about, you know, in the US alone, right? Hundreds of thousands of patients die from really preventable issues. What about the ethics of that? So I know it's not an easy question, but maybe I'll hand it to Mike since you're farthest away from me. So what about the ethics of not deploying AI that is ready for prime time, that is reasonably without, you know, contention? What about those sort of easier elements of AI and not deploying it to prevent errors or prevent, you know, interactions of drugs that should have been picked up, you know, things like that? What do you think about that?
Well, I don't think this is a different problem from deploying any procedure or technology that is known to be of benefit. And of course, frequently with these things, the barriers to some of these things are very human and not technological at all. And in some cases, those human factors are well justified, and in some cases they really aren't. And it's just to do with, you know, I don't like it, I don't fancy it. And I think you have to be pretty robust in challenging those views, while all the time, of course, remembering to listen, because refuseniks are sometimes right. And that's one thing that I have learned over time, that, you know, I have got somewhat better at listening to people who are saying no. Don't necessarily agree with them, but I do listen a bit better these days. I think the problem is made somewhat simpler by the fact that an awful lot of the things that we know actually could be prevented very, very easily by what falls under the heading of AI, are actually quite simple things. They only require the relatively easy end, if you like, of AI. Because one of the things I'm very interested in is, you know, when we talk about this, we're talking about such a broad church of things, many of which are trying to be taken into production at the moment, are actually quite straightforward. I mean, they're often little more than putting known sets of guidelines in front of people in an immediate way and applying it to that patient. And so really, you know, in cases like that, there's really no objection to, or there should be no objection to, introducing a technology which simply makes it easier for clinicians to follow existing guidelines that have been drawn up by committees of highly expert and experienced people. And I think at that sort of end of the technology, saying that I'm not doing this because it's a computer is really quite indefensible. And I think should be regarded in much the same way as any other form of indefensible medical practice, quite frankly, or refusal to follow guidelines. Now, of course, the problem is that what we call artificial intelligence then goes through a whole spectrum of increasing complexity, decreasing transparency, and you know, ways in which it's very difficult to know how they behave in the real world. So, you know, the simple sort of application of a decision tree that implements a guideline, it goes at one end, and then you move through sort of convolutional neural networks, general adversarial networks, into supervised learning and ultimately deep learning. And I think the thing that we need to get to grips with is that what's going on in terms of both the ethics and the safety at one end of that spectrum is completely different from what's going on at the other end. So when I'm thinking about clinical safety and ethics and so forth in this area, I sort of think of that continuum. And at one end, I think the situation is relatively straightforward. The ethics is just essentially to do with the same as applying a guideline. You know, that's what we should do unless there's a good reason not to, in which case you justify why you don't do it. And then as you kind of move through, the situation does become murkier, and probably the tests that we'll need to apply in order to determine the safety and ethical status of those sorts of technologies will change as well. Because at the sort of far end, you know, the deep learning sort of end, clearly you can't apply the same sorts of tests and checks and balances as you would at the other end of the spectrum, where probably really quite traditional clinical safety and engineering safety procedures would be okay.
I'm going to throw a complicating factor in here, Mike. What if the guidelines are not the best practice and we just think it is because an august group of experts deem that it is? And I often find that to be the case, actually. The clinical guidelines are either outdated or just people in the room decided that they know enough as a group to represent the entire profession. Unfortunately, I've been on both ends. And it's turned out not to be correct, or turn out to be very counterproductive, or turn out to be no benefit. So we need to just, I think, maybe couple the data in the real world with what the experts have thought in the past or present, and just have a balance, right? Because they could be wrong. Yeah.
And absolutely. And the guidelines, you know, not infrequently are wrong, of course, because they're, you know, although we like to think in medicine generally and in cardiology in particular that we're all following the science, is a phrase which is very popular at the moment in my country. The question, of course, is which science, and also which scientists, because scientists are humans as well, and they have all sorts of motivations which are not simply driven by data.
Yeah, we're just starting to, when we have retreats on research, we're just starting to say, well, data scientists are actually scientists that belong under research also, right? Not just your traditional benchtop or clinical researcher. So, Charitha, how about you? What do you think? How do you bound? You're among the younger contingent, and this is going to be your platform and your legacy. How do you see as a young person in the middle of all this?
Yeah, I think it's an interesting point. I was just thinking about how in some ways the transition to AI is not similar and much more complex, but is in some ways analogous to how we transition from maybe written notes to an EHR and then kind of going from there. And I think at that time, you know, there were many people who were not trusting of that transition to go from their standard written notes to an EHR. And I think most people would argue that the benefits, though there's still some painful aspects of an EHR, that the benefits for both patients and clinicians kind of outweigh that transition. And I think AI will probably have a similar kind of thing. And I think we have the added benefit of a general population that's also quite engaged in that. I think that the general population is worried about privacy, and we're seeing that in all the other fields, not just related to, you know, healthcare. I think, you know, there's so much going on in terms of just internet privacy and you know, how that applies. But at the same time, you can see that patients with all their iPhones and all the data that they're planning to send, they're happy to do that, it seems. Many of them are sharing EKG data or health data automatically, not thinking necessarily. I think there's a ton of regulations that are associated with hospitals that it's hard to figure out at which point are we supporting the patient's desire to really use the most advanced technology, but also regulating how the AI could compromise their privacy, and at which point do those converge and diverge to make sure that we're really giving them the opportunity of using the advanced technology.
Well, since the technology is almost exponential in this sector, I do feel like what we talked about, which is regulatory, legal, ethical discussions, have been relatively straight line, and we need to really pick up the pace, which is good. I think we're definitely seeing that. So Agil, from the industry perspective, are you seeing, do you think regulatory has eased a bit and trying to accommodate this surge of technology?
I don't know necessarily if I would say they're eased a bit, but I think it's important that the regulators are make informed decisions and informed regulations around this. And I think definitely the FDA has come out with very good and thoughtful guidelines and documents lately. European regulators are doing the same thing, maybe a little bit behind. I mean, we definitely need regulation and make sure we don't do real harm to patients here, right? Yeah. I just wanted to pick up a few words that, has been mentioned here, transparency, accountability, explainability. I think that this is important when it comes to AI. We need to, since it's based on data, we need to have some transparency in terms of what data were used during training and during validation. And I think a little bit earlier today, the question came up. So if the AI model really works, who cares about explainability? And to me, this is really about the level of evidence that should be required for clinicians to trust it. If there's a black box solution, you need the highest level of evidence. You need really that assessment and validation to make sure you can trust it based on its performance. If you don't have that level of evidence, you really need to provide explainability and allow the clinicians to reason about whatever result or recommendation the AI is giving. So I think that we may be able to have different levels of evidence, but it sort of ties into the level of transparency and explainability, because these really black box solutions, they will require a high level of evidence, in my opinion. And I think that's correct. We need to make sure that these models work well.
Do you think we have explainability for pacemakers or echo machines for cardiologists? Even though we get tested on it on our board exam, I don't think people have kept up.
No, I see your point, and I do agree to that to some extent. But still, you can reason about those images that you're seeing. You can reason about whether they are artifacts or real, or what you're looking at there. So there is some level of transparency, although you may not understand the beamforming. You can reason about the images you're looking at.
Yeah,
I was going to say that the explainability, though, is that much different than expert opinion to a certain degree, right? Because like you were saying, it's a few people in a room making a decision that could be informed by all sorts of biases of what they've seen or whatever it is. So it might be just as murky as the explainability of an AI model. I think it's harder to swallow, but it might be the same.
That's exactly what I say, because I'm often, even though I don't want to be a defender of machine intelligence, I'm often on that side. And I always say, if I were a machine, I would say to the humans, you call us black boxes, we can call you pink bags. We don't know how your brain works, and even humans don't know how the brain works sometimes. And those of us who have been long enough in clinical cardiology, sometimes you make an amazing decision and your trainees are asking you, how'd you come up with that? And you struggle to explain all the steps, right? Like an algorithm, and there's no algorithm, right?
But you can
Anthony,
right?
Yeah, Francisco.
Think about this. If you would have in front of you an algorithm that would predict the stock that is going to double in price in the next 6 months, and it's pretty accurate, 90% of the times, you will not care whether you understand the underpinning of the, tell me the name, because that's going to make a difference in my retirement. No, but let me mention something else.
Or presidential elections, right?
For example, yeah. No, but regarding your question about it is ethical to withhold AI, again, we have to be careful before we conclude that something truly works in the field, because efficacy research, as we know, is different than effectiveness research. And let me just share briefly data that is going to be presented at the AHA in 2 weeks by one of my colleagues here, Peter Noseworthy. We actually, we were so excited with this low EF algorithm that we developed randomized clinical trial. We randomized almost 400 practitioners, okay, with about 20,000 patients that got an ECG. And the randomization was, you will get the flag saying your patient might have a low EF, or the EF is likely normal, or you will get nothing, just the ECG as a standard. Guess what? The intake and the uptake of the new information is not as robust as we might think. Clinicians, 40% ignore the flag. Okay? So, and you're talking about, physicians working in a medical center, and, people that are used to innovation and all those things. So that's another area where we have to keep working, which is educating clinicians that, once you have something, it actually good. It is good. Or may change your practice, and you have to believe if there is a publication out there showing the results. Why don't you believe this as much as you believe in a PSA antigen? They say, well, because you have to do 3 echoes for every single low EF you detect. Well, you have to do 12 prostate biopsies to find one cancer, because all of the other 11 high PSAs were false positives. We are so okay with errors with biomarkers, and we are so strict with errors with AI. There will be no perfect algorithm that predicts 100% accurate.
Yeah, we're often asymmetric in our expectation. And those of us who are in pediatric cardiology knows that there was a study that showed, roughly speaking, EKGs with very hallmark findings for certain diagnoses were missed up to 35-40% of the time by pediatric cardiologists that know their diagnoses in the stack of EKGs. So, but yet 0.80 on the AUC, we're saying that's not good. So it had to be a little bit more fair to the machines, right? That they're fallible and that we accept their fallibility. So, and then the ethics, of course, of, this is one of the top 10 questions I get, which is a clinician is almost entirely reliant on an algorithm to help make a decision, and then who's culpable if there's an adverse outcome that was clearly related to that decision? Is it the clinician? Is it the algorithm, the company that sells the algorithm, or is responsible, or is it the data scientist that came up with the algorithm? So, what's your take on that? No human is stepping forward, I see. It's my fault that I believe the algorithm, right? Yes, Mike. Mike.
Yeah, I mean, I think, like you say, this is going to resolve itself around an acceptance that nothing is perfect, including us. And, if somebody has a positive PSA, and then has a complication during their prostatic biopsy, nobody's asking at the moment, should we be suing, the person that did the original research into PSA, or the company that made the PSA assay or whatever. It's just an acceptance that things are, they have finite sensitivity, specificities, and positive and negative predictive values. And I think I suspect in the end that it will be the ultimate responsibility will rest with the individual clinician or their institution, but with an acceptance that if they believe in AI, they're simply using a tool which has known limitations and strengths. And if it's been shown that the strengths are greater than their limitations, then that is a right and proper thing to be doing.
Yeah. I do find it interesting in my 6 years of doing AI medicine meetings, that each time when I do an audience poll, pre-COVID, that the number of people that will raise their hand for each of the technology milestones that I talk about, the autonomous driving vehicle, when I first started, almost no hands would go up 5-6 years ago. And now it's the majority in a space of 5 years, which is pretty amazing to me. And traditionally, I haven't gotten any hands raised for autonomous flying vehicle. And now, surprisingly, depending on the audience, it's usually a quarter or more. autonomous flying vehicle with no human pilot. So it's definitely getting there in terms of a tipping point. But I just want to mention that, I kind of read up on technology history, and I don't know if you're familiar with the history of elevators when it first came out. No one would ride the elevator without a human operator for a very long time, I think decades. And my parents still talk about, having a human operator, and some hotels in California still have that. So, but do you know what it finally, why did humans finally accept just riding in an elevator without a human operator? It's an interesting little story. What was the tipping point for humans just to get on an elevator without a human operator? It wasn't improvement in technology. It wasn't trust or whatever. Yeah. Human operators went on strike. And then people just got tired of walking up long flights of stairs. And then they decided that potential risk was not worth, all that extra work to go up the stairs. So slowly but surely, humans fell online and started riding elevators without a human operator. Of course, that was terrible for the human operators. They never would have thought that humans would trust the elevator to that extent. So there's some interesting analogies for what we're doing, is that, I think trust it within reason and with a lot of scrutiny. But as Bill Gates says, please don't let that slow progress down, because it's so important that we embrace this technology that's well ahead of schedule, but we just have to be careful with this important resource. So I'm going to go around very quickly in the last 2 minutes. Last tweet from you guys for our audience to remember. Jaritha, I'll take you with your facial expression. You're ready to go, I can tell.
No, that was my, oh God, I don't know what I'm going to say for this.
Can we come back to you?
Okay. Yeah, sure.
Okay, Francisco, you're used to being under pressure. What would be your message for our audience of cardiologists?
Sure. For people, be open to new information, but at the same time, stay very critical of new information.
Great.
And AI.
Mike?
Yeah.
Mike?
I think I would say, don't fall into the trap of thinking that things have to be perfect to be useful. We don't apply that test in other areas of medicine, and we shouldn't do it in this one either.
Hey, Gil?
I think being a company representative here, I will say to the clinicians that, work with us, reach out to us. We have the same mission. We want to work with you guys to make this happen together.
Well said. I like that. Kathy?
I think it's going to go really quickly, very quickly, that quality of an institution, quality of the care it provides is going to require that you're actively using surveillance of your system or improvement of your diagnostics using these new tools. I think that shift.
Are you ready? Thanks, Kathy. Are you ready now?
Yeah, mine's pithy, but it would just be trust, but verify broadly.
I will predict that 10 years from now, when I invite all of you back for AIMED Cardiology in 2030, we will look back on this conversation and say we totally underestimated the capabilities, that we were still talking about medical images, and the new generation cardiologists will not be talking about deep learning for medical images because they'll be embedded so deep that it's just routine practice. So with that, I want to thank all of you, my amazing stellar faculty and attendees out there. Please be safe, and cannot wait to see all of you in person and have a very special AIMED Cardiology. So goodbye, everybody.
Bye, everyone.
Bye.